Sir, good morning, sir. Am I audible?
Yeah, I can
sir,
hear
you are
you.
audible.
Yeah, thank you very much, sir. So, thank you, sir. Good morning, Dr. Harshad, sir. It was nice to see you early in the morning. So, on behalf of Computer Science and Engineering Department, Gndecb Engineering College, Bidar, I welcome Dr. Harshad Khadilkar and all the participants who have joined on this lovely Saturday morning uh, for witnessing a fantastic session from you, Harshad sir. Okay, so thank you very much, sir. So just let me share about the Harshad Khadilkar, sir. So Harshad Khadilkar, sir, has completed his PhD in uh, aeronautics and astrostatics from Mishashan Institute of Technology. His advisor was Professor. His advisor was Professor Hasma Balakrishna, and his thesis was network control of aircraft operations and airports and in terminal areas. So he has completed his SM in aeronautics and astronautics from Mishashan Institute of Technology again, where he had his thesis on analysis and modeling of airport surface operation. Sir has completed his BTech in aerospace engineering from the prestigious institute, that is the IIT Bombay, where he had carried out his final year project on multidisciplinary design optimization for the design of the flight vehicles. Sir is presently working as the TCS research as a senior scientist and team lead for the planning and control since from March 2021. Earlier, he also worked as a scientist and the team lead planning and control again at the TCS research in Mumbai from May 2015 to the February 2021. So where he was been involved in developing the AI solutions for transportation, logistics, robotics, and the supply chain. Sir also works as a visiting associate professor in the Department of Aerospace Engineering of IIT Bombay from March 2019 till date, where he covers the topic in modeling, simulation, machine learning, and aircraft design. Sir also works as an associate researcher in the Robert Bosch Center for the Data Science and AI at IIT Madras from November 2021 to the presently. So where he undertakes the student mentorship, lectures and workshop organization. Sir also works as a research assistant at the IBM Research Lab, Bangalore, way back in the year 2013 to 2015, where he developed the algorithms and the methods for the efficient utilization of the electricity. So this is just a brief profile of Dr. Harshad Khadilkar, sir. He is a young and very dynamic scientist who is giving his contribution with this artificial intelligence and machine learning. So we are very fortunate to have you in this session, sir. So on behalf of Computer Science and Engineering Department, I welcome you, sir, for this session. Thank you very much for joining the session, sir. And over to you now, sir. Please, you can carry on your session, sir. And we'll be very eager to learn something from you, sir. Definitely.
Thank you,
sir.
So we are going till 11, right? Maximum?
Yeah, yes, sir.
Okay.
We can, sir.
Yeah.
Up to 11.
Okay. Thank you for the introduction. And just so everybody is familiar, you can just call me Harshad and interrupt me if you have any questions. Okay. So the more interactive our session becomes, the more interesting it will be for everyone. So if you have questions, just pop up and ask them at any time. I'm going to start. First of all, I'll stop my video while I'm doing the slide share because sometimes there is a mismatch, and I'll start sharing my screen. Let me know once you can see it. Yes. Can you see my slides?
Yeah, sir. We can, sir. That is
Okay.
AIML for decision making in industrial application. Yes.
Okay. Excellent. So thank you for inviting me here, and I'm going to go into why we need artificial intelligence or machine learning for improving industrial operations. The plan is to go slowly from the basics and the motivation into more technical topics towards the latter part of the lecture. But I mean, if at any point you feel that this is too basic and you're already familiar with it, you can let me know so we can go ahead quickly and then spend more time on the technical portions. Okay, so first of all, I think everybody's heard of this concept of Industry 4.0, which is the four different revolutions of industrial production. The first industrial revolution really was when we mechanized power so that we could utilize steam and coal to improve the amount of work that we can do given the human power, existing human power at the time. But what's important is at the bottom of the slide you will see what's happening on the mathematical and algorithmic front parallel to these industrial revolutions. Okay, so when the first mechanization took place, we were looking at basic science, how to understand physics, chemistry, how does coal's chemical engineer energy get converted into power, mechanical power, and so on. In the second industrial revolution, towards the beginning of the 20th century, we had mass production of goods and vehicles. So Henry Ford's car production line is a very famous example. And at the same time, because these vehicles and goods were being manufactured, many different parts coming together from many different areas and coming together on the assembly line, so you need a constant supply of all of these different parts at the same time. And so the birth of operations research took place, which was the first time you had optimization problems, the resource allocation problems, scheduling problems, all of those started being looked at in the early part of the 20th century. Then the latter half of the 20th century was about programming skills, because you had robots coming in on these assembly lines. So there were no longer people doing all of these little jobs, but there were robots doing the same repetitive movements over and over again. So there was automation, but there wasn't so much intelligence, right? Because the robots were doing the same movements over and over and over again. And the advantage of these machines was that they could do it much more precisely than what a human could do. And so to program these robots, to program the individual movements of the robots, we needed programming skills. So all of our programming languages came up: Java, C++, and so on. And now we have, in the 21st century, we have entered the realm of cyber physical systems. So these are physical robots, but they are now connected over the internet to each other, and they can coordinate to do much more adaptive or intelligent things. Okay, so for example, you might have cars that are coming up in the very near future, in the next 5 years, where you can specify everything about the car. Okay, what type of headlight you want, which engine you want to use, what color upholstery you want, all of that you can specify. Now, you can already do this in the US if you're buying a Tesla, and the robot is able to manufacture that car to your specification exactly. Okay, and so every car that comes up on the assembly line is going to be different, and the robots have to coordinate to make sure that all of them are correctly manufactured. So now we come to the point that we can no longer have specific programs or instructions written for the movements of these robots. To some extent, they have to figure out what needs to be done on their own. Okay, and so for this, we need artificial intelligence or some kind of algorithmic framework that can help the robots coordinate with each other effectively to do different or variable tasks. Okay, so that is why we need artificial intelligence these days in industry at all. And the reason is that we can no longer do repetitive or instruction or prescriptive things. We have to let the machines figure out to some extent how the problem needs to be solved. Okay, so that's why we are thinking of even going into AI for the future. It is not just something that is cool or trendy at the moment. So, from all that we have seen in literature and in industry so far, these are the things that AI is probably going to take over. That's the top row on this slide. Okay, so AI will probably take over tasks that need to be done too fast for a human to handle, or those that are too repetitive. So, the same movements over and over again, which can be fatiguing for a human being, uh, or things that are too dangerous, such as maybe going into a disaster area using an unmanned aerial vehicle to find the victims of earthquakes or floods. Okay, a task that need to be done too precisely for a human to handle. uh, and now the last two are really the main focus of AI based things. Okay, so the first four things you can imagine that even a pre-programmed robot will be able to do, but the last two, handling very large quantities of data and figuring out what needs to be done, which is the quantitative task that I'm looking at, this is really something that you need an adaptive algorithm or a learning based algorithm to do. And similarly, to solve a task better and better, focusing on a specific task and improving your performance on it is also something that artificial intelligence is able to do, and traditional programming algorithms or optimization algorithms are probably not able to do. Okay, and the reason is that once you specify an optimization algorithm, there is no further improvement that will happen on its own. You will have to change the formulation in order to get a better solution. Whereas with machine learning, the problem specification itself can evolve by itself. Okay, at the same time, there is a worry that AI might be taking over too many tasks that humans are currently doing, leading to job loss, etc. I don't think that really is a very large risk. What will happen is that the jobs on the top line, the fast, repetitive, dangerous, etc., those jobs will probably be taken over. But at the same time, a lot of jobs that humans are very capable of doing and that AI is not good at. Okay, so things that are creative, unstructured. So, for example, looking at art or doing, call center kind of work where you're trying to solve somebody's query when they're upset. Okay, so these kind of things that you where you need to intuit somebody's emotion. Yes, is there a question? Okay, when you have to handle, sorry, when you have to handle somebody's emotions, intuit what they exactly need, or when you have to generalize. Okay, so if you're teaching somebody, then especially in a school, then say very young students could come up with any sort of query, okay, which may or may not be related even to the topic. So to handle questions like this, it is very hard to have an AI based algorithm solving them. You need to be more flexible, generalized, etc. So these are things that humans will keep doing. Okay, and the really exciting part of AI for the future is that we will see human capabilities being enhanced by AI rather than being replaced by them. And so we expect that we'll be able to do far more with the same amount of resources than we can currently do. Okay, and that's where we are trying to move as researchers in the field of AI. So very briefly, just one slide on what we are doing in TCS research, what my team does, and what I've been doing for the last 5 years is we have been trying to deploy AI ML. There's a typo there; it should not be AL; it should be AI ML algorithms uh, for improving industrial system efficiency efficiently. Okay, so the first part of this industrial system efficiency is quite clear. It is any industrial system that you can think of: transportation, manufacturing, retail, supply chain, logistics. We look at operations in those industries and try to improve them using data driven methods. So that's clear enough. The novelty that from our perspective is that we are trying to do this efficiently from the point of view of computational resources and time. Okay, so a lot of work you will see reported in popular, in the popular press, magazines, etc., Google, Facebook, requires a very large amount of compute. And we'll come to some examples later when we look at specific case studies. But we cannot always invest that much amount of compute to solve every problem. A, because it may not be economically reasonable to invest that much amount of money to get a small amount of improvement, and two, because not many companies or even countries are able to invest a huge amount of money to solve a given problem. So you have to use a reasonable amount of compute only. And so we are trying to look at how do we use a small amount of compute, say one server or one laptop even, to come up with solutions to these problems. Uh, to come up with solutions to these problems uh, we, in a reasonable amount of time. And the way we do that is by having the humans who have been operating the system. So if you look at, say, a railway scheduling problem, then we already have railway controllers who operate our railway lines today, correct? And they have more than 100 years of organizational experience in handling India's railway lines. So we say, why should we replace all of that intelligence directly with a computer who has learned from scratch? What we can do is we can use these people's experience to decide what are the important things in a railway scheduling problem, what aspects need to be looked at. Okay, so is it the priority of trains that is important, or is it important to schedule very complex junction stations first and then the rest of the line is easy to do? Okay, so all of these insights come up from the humans, and so we can design these AI/ML algorithms to take advantage of this from the start. That way, a lot of the learning is already kind of short circuited, and then we can work in a complementary fashion with the existing operating rules. So if there is a rule, a thumb rule right now that the controllers use, which says a Rajdhani should always be given priority over other trains so that you don't have to slow it down, we can see if that is a good, starting point for training an AI/ML algorithm. So that's what we are trying to do right now, which is this is the system of today. Okay, the blue box that you are seeing, it we know that it has already got a very large number of sensors in place. Okay, so SCADA systems, etc., are already installed on most large networks. Okay, so if you look at a power network or a transportation network, so there is a lot of data, big data, IoT sensors on these systems already, which generate a huge number of these possible important features in the data. And even today, there are many machine learning or AI algorithms which can do prediction, forecasting, alert generation in case of some anomalous behavior. But all of this information, all of the predictions or alerts are sent to a human being who is in the loop. Okay, they are sitting in the loop. And so every time information is received from these algorithms or from the IoT sensors, the person has to take a decision as to what needs to be done to improve the system's performance. Okay, and from our perspective, this person is very critical because they have intuition and experience, like I said on the previous slide, which we cannot really train into an AI algorithm. But on the other hand, it's also a bottleneck because in normal or day-to-day operation, waiting for a human to take a decision is creating a lot of delays. Okay, so what we want ideally to do is to move this person up into a supervisory role. Okay, not keep them in this closed loop portion of the system, and say that we will replace it by an AI or ML algorithm to take day to day actions while the person observes what is happening and intervenes if required. Okay, so is that clear what we are trying to do in the today's lecture, what we'll be trying to focus on? So we will not be handling any out of the way kind of things which it is anyway difficult for an AIML system to handle, because you have to train the system before it can work in that kind of regime. We'll be focusing on replacing day to day operations and then having a supervisor for intervention if required. Yeah. Is there a question? Okay. So this is really the contrast between what AIML does and what the programs of today, the state of the art today does. Okay, so we are going to say that, and first of all, everybody has a different definition of what machine learning or AI is. So I should make clear what I am talking about when I think about AI and ML, at least in the context of this lecture. So in my opinion, a system can be called to use artificial intelligence if it can adapt its outputs to the same inputs. Even if you give the same inputs again and again, it can adapt its outputs and improve them as it observes more data. Okay, so as it observes more and more data points, even the same inputs produce different outputs. And this is the key difference between what state of the art today does and what AIML kind of algorithms do, right? So this is an example. So there are two, principal ways in which systems of today work. So if you give a very simple example, that you are giving it two numbers and you are expecting a single number as an output. Okay, so I'm giving 2 and 2 as the input to the system, and I'm saying the output is 4. If I give 3 and 3 as the input, the output is 9. Okay, so these examples are known to the system already. Now the point is, if I give a new input which is 4 comma 3, what output should we get? Okay, so the two principal ways in which the systems of today work is, they will look up in a database whether there is an example that matches 4 comma 3. Okay, so if there is a matching example, it will return the answer. If there is none, then it will say the example was not found, data not found. There is a programming based approach which says, I'm going to guess what is happening to these inputs when the output comes out. So if you look at them, there could be multiplication. Okay, so the first example is not very easy to figure out, because it could be addition of the two inputs, it could be multiplication of the two inputs, or it could be square of the first input, right? All of them would give you the answer 4. But the second input narrows it down, so it is 3 comma 3, and the output is 9. So it cannot be addition, but it could be multiplication, or it could be square of the first or second term. Okay, but I'm going to guess and say it is multiplication. So if I give 4 comma 3 as input, I will return 12 as the output. Okay, and so this is fixed in my code. Whenever the two inputs come in, I'm going to multiply and return the answer. So now what happens if I give an additional data point? Okay, and any of these is a reasonable output to get. So I could give it 4 comma 3 and get a slightly noisy output like 12 comma 1, 12.1, which is possibly 4 times 3, but with some plus minus kind of noise. I could give 4 comma 3 the output as 12, which is multiplication of the two, or I could get an output of 16, which is the square of the first term. Okay, so there is no way in these two methods to do adapt to this additional data point automatically. You have to go and change the code. Okay, and this is what AIML is able to do. It is able to adapt to new data points as it observes the input and output pairs. Okay, so this essentially is what we want, the right hand side diagram, which is, we want to use human knowledge, all the domain expertise that exists in a given system. We want to use the systems or the algorithm's own curiosity and exploration. Okay, so it wants to explore, giving out different answers and asking the human being, was this right, was this better or worse, etc. All of this is going to be done offline. Okay, so it is not going to do this when you actually specify a new problem for it. It's going to do this during initial training, and then both of these boxes result in aggregated intelligence in the system, which will be the basis of all the decisions that the AI algorithm takes in real time when you give it a new problem. So, for example, if you give it a new railway schedule or today's railway status, where all the trains are and how delayed they are, etc., it should be able to give you one shot solution for how those trains should be moved so that they come back to their original timetable. And it has to do this fast. Okay, so it cannot do exploration, optimization, etc., in real time. When you specify a problem, it directly gives you the solution without having to think about it. And the reason it doesn't have to think about it is exactly the same reason that you and I don't have to think about a new problem, right? Because we have done the training, we have muscle memory, our brain remembers what needs to be done. That is exactly what we want to do for the AI algorithm. We want to give it muscle memory, we want to give it prior training so that it knows what needs to be done in real time. So now I'm going to specify exactly what kind of machine learning I'm thinking of when I say that we want to take real time decisions. Okay, so since everybody is done, I think 3 days, 4 days of AIML already, they will have seen this a lot, right? There are three types of machine learning: supervised learning, where the goal is simply to minimize the error with respect to the right outputs. Okay, so the system produces some output, there is an ideal output which you want to match, and so you try to minimize the error between your output and the ideal output. So all your classification, regression tasks, etc., are part of supervised learning. Unsupervised learning is where you want to find patterns in the data. So there's no right or wrong answer. What you're trying to do is analyze the data to see what are the similarities or differences between different points. Okay, so I'm going to call this analysis. And there is a third type of machine learning called reinforcement learning, where the focus is to take actions that maximize some long term rewards. Okay, so there's a long term goal, and you want to maximize the reward you get while chasing that long term goal. And that is really important. So, the long term part of it, I mean, the reason is that it is no longer one data point as input and one output. Okay, you are trying to do this over many time steps, a sequence of decisions that lead to a long term goal. Okay, so this is why reinforcement learning is generally considered to be a much harder problem than either supervised learning or unsupervised learning. And the reason is that you don't get the answer in one step. You have to do this, lead the algorithm essentially through a very large number of sequence of decisions to come up to your whatever your long term goal is. Okay, so to make it more real in the railway context, you cannot just move one train and be done with the answer. You have to move, if you are in a delayed state, you have to move maybe 20, 30 trains for over half an hour before those trains have finally returned to the original timetable and they can move according to whatever the timetable says. Okay, so that's the difference between reinforcement learning or RL and other types of machine learning. So conceptually, this is how it works. Okay, so you have the learning agent, okay, which is whatever algorithm you choose to put into your AI system. And we will come to exactly what goes inside a learning agent in a few minutes. But there is some kind of algorithm which can adapt to whatever observations it is making over time. Okay, so for now, we'll just call it the learning agent. There is an environment in which it is operating. So this environment is whatever system you are trying to control. So if you recall the similar flowchart that I'd shown you a couple of slides ago, there was a system here, and then there was an AI/ML algorithm which we said we want to put to take day-to-day decisions, right? So this is the AI/ML algorithm that is going to take day-to-day decisions, and this environment is the system that we are trying to control. Okay, how does the system tell the learning agent what needs to be done? It does this through two signals. One is the state of the system. So all of the important information that exists in the system is sent to the learning agent so that it knows what state the system currently is in. And it also gives it a feedback called rewards, which we'll come to in just a few seconds. Okay, so first of all, let's assume that the information about the system is given to the learning agent. The learning agent takes a set of actions after observing this information. Okay, so for example, if you're doing autonomous driving, you observe the state of the road, where the other cars are, whether there are any pedestrians that are crossing the road, and you give out a set of actions, which is where the steering wheel should be kept and what happens to the brake or the accelerator. Okay, so these actions are given to the environment. which implements the actions and gives it a new set of information, which is the result of those actions, right? So this state action loop is closed and it can continue for a long time. The way the learning agent is going to improve the actions, okay, how it's going to adapt to newer and newer states is by observing a set of rewards, which is how the system evaluates the current state to be. Okay, is it coming close to the goal? Has it breached any constraint? So, for example, has the car drifted across the lane to some other lane which it should not have, and so on. Okay, so all of these things are given as feedback in the form of reward to the learning agent. So, the goal of the learning agent is to take complete the state action loop, the closed loop, while trying to maximize the rewards it is getting from the system. Okay, so the reward is the performance measure of your machine learning algorithm. The states and actions that you observe in a sequence is the experience that you are going to use for training. And the task is to come up with the optimal actions given the states that are being observed. Okay, so this is the concept in a picture. We will kind of make it more technical in a few slides. In fact, in this slide itself. So far, can we just do a quick sound check to make sure everybody is on board? Are there any questions? I'll take a very brief pause to wait for questions.
You're audible, sir.
Clear questions.
Yeah, was there a question or okay? Okay,
No questions, sir.
okay, fine. Okay, so I said on the previous slide that we are going to try and maximize the long-term reward that we get. Okay, and this is how we typically define the long-term reward. So in every time step, we said we will get reward as a feedback, correct? So I'm going to say at time t, the reward we get is the value rt. Okay, this is just a number, a scalar number. But we are not just trying to maximize RT, which is the current time step reward. We are trying to maximize the long term reward. And so what we'll say is we are also interested in RT plus 1, RT plus 2, etc. Okay, all the way to the end of the task or up to infinity if the system never, if it is a 24/7 kind of system. Now, the future rewards are not given the same importance as the current reward RT. We are going to call this gamma a discount factor. And so the future rewards are essentially discounted as you go farther and farther in the future. So the next step reward RT plus 1 is weighted down by gamma. Two time steps from now, it is going to be gamma square and so on. Okay, so you will see that even if this is an infinite number of terms, because gamma is going lower and lower value, gamma is always less than 1, the sum of all these rewards will still be finite. Okay, so discounting helps us keep the reward finite, as well as it's a very realistic thing in the sense that when you look at money today, money in your pocket today and money in your pocket in the future, you tend to discount future uh, returns to in order to maximize your today's earnings. Okay, so the maximization goal is not to maximize the reward in the current time step, but to maximize the long term reward which is given by this expression. Okay, and the this specific expression with gamma, gamma square, etc. is called the return in reinforcement learning terms. So GT is called the return, whereas RT is called the step reward. Okay, so this is how the reinforcement learning problem works in the diagram. Okay, so you observe the state at time t, it is given to the agent. The agent produces the action at time t, which goes to the environment. The environment gives it the new state, which goes again to the action and state action, etc. So this cycle continues. Oh, sorry. At the same time, the environment will also give the reward from the previous time step. Correct? So you'll observe that this is the state at time t plus 1, but the reward given is for time t, which is the previous action. Okay, so there's RT plus 1 and so on, whereas the state is t plus 2, t plus 1, t plus 2, and so on. And instead of minimizing the error, which is what we do in supervised learning, we are going to maximize the reward. Okay, so we are going to maximize. Now we can make this more precise and say the reward in the long term, we are trying to maximize the return, GT. Okay. Now, an important caveat in what all the things we are saying, okay, is that we have to assume that this process is called a so-called Markov process. Okay, and the reason we have to do that is because we are assuming whenever we are training this RL agent, we are assuming that the state at time t and the action you took at time t are the only two things that influence this reward. Correct? You will observe that RT does not have an arrow, incoming arrow from a very older state. Okay, again, RT plus 1 does not have any incoming arrow from the state at time t or action at time t. The only information it is getting is from the state at time t plus 1 and the action at time t plus 1, which is gone to the environment. Okay, so to make sure that this assumption is valid, we have to assume that the system is Markov, or that previous states and actions do not influence the reward you get in the current state. Okay, and this is an example kind of contrasting between a Markov system and a non-Markovian system. Okay, so if you look at the chessboard is Markov because it does not matter how you came to this distribution of pieces on the board. Okay, it does not matter whether the in the previous step your queen was killed, or whether the rook was killed, or a pawn was moved, whatever it was, right? So long as you can see this snapshot and you know that black is the one who is going to play the next move, you are you have all the information you need to play chess from this point onwards. Okay, so this is a Markov system. On the other hand, if you look at on the right hand side, this cart pole problem, where there is a cart on wheels and there is an inverted pendulum with a mass on top. Okay, so the goal is that you move this cart to the left or right so as to keep the pendulum balance above. Okay, inverted, it has to be kept standing. Now, if I just give you this photograph and say, tell me where the cart should move next so that the pendulum stays up, you will say that I don't know whether the cart is already moving to the left or right, and whether the pendulum is falling to the right, or whether you have already accelerated this cart to the right, so the pendulum is already moving to the left. Okay, so until you know what is happening in the last few time steps, which will help you know whether the pendulum is coming down or whether it's going up, you will not be able to tell me what action should be taken on this system. Okay, so this is a non-Markovian problem because you do not have enough information just from the current state to know what the next time step outcome will be. Whereas in chess, you had all the information you needed to know what the next outcome will be. Okay, so this is a Markov system, this is a non-Markov system. An interesting and simple way to make the right hand side a Markov problem is, if I tell you, apart from this picture that I'm giving you, what is the angular velocity of the pendulum and what is the linear velocity of the current. Okay, so I give you two pieces of information in addition to this picture. As soon as I do that, the problem becomes Markov, because now I know whether the pendulum is falling down or whether it's going up, and whether the cart is moving to the left or right and with what velocity. Correct? So it's not that if you have a non-Markovian system, everything is lost and you cannot use reinforcement learning. You just have to think of a better state space representation to make sure that the problem that you're actually solving is a Markov problem. Okay, so this is a graphical illustration of what I was talking about. So there is a time step t at which you get the state st, right? From there, assume there are only three possible actions you can take. Okay, so you can do x1, x2, or x3 as the three possible actions. So each of those actions will lead to a different step, different state at the next time step. So if you take action x1, you will end up in this state st plus 1. If you take x2, then you will end up here. If you take x3, you will end up here. right? So there is essentially a branching behavior that we see when we are going through this reinforcement learning episode. Okay, so every time you suppose you take state action x1, you end up here again. You have three possible actions, and then you keep branching out and out. And what we are trying to say is that we want to take that sequence of actions such that we go through this tree while gathering the maximum possible reward. Okay, and we want to figure out mathematically how we will solve this problem. And this is where we start looking at how we actually solve the problem. So this gt equal to rt plus gamma rt plus 1 etc. is the expression we had written earlier, right? That we want to maximize this return, gt equal to rt plus gamma rt plus 1 etc. Now what we are going to say is that we don't know what the actual return gt will be, okay, given the current information, but we want to build a machine learning algorithm to guess what it will be. My current state st is given. I want to know what action I should take to maximize the return. So I'm going to say I'll define a machine learning algorithm which can predict, given the state I am in right now and the action I propose to take, I can predict what this value of gt will be. Okay, so this becomes a very familiar supervised learning kind of algorithm, correct? So if I give you state and action, I want to get the most accurate prediction as possible of the return from that point onwards. And this q value is the value of gt that we are predicting. We are predicting that gt will be equal to q of st comma at. Now you can think of this programmatically as q being an actual function in your program that takes as input two variables st and at and gives returns a scalar value gt, which is the prediction. Or you can think of this, if you have already done neural networks deep learning, you can think of this as a neural network where st comma at is a concatenated input that you are giving to the neural network, and you will get the q value, the scalar, as a single valued output, a single neuron in the output layer, and so on. Okay, but you will agree with me, I hope, that you can do this programmatically. So you can train a machine learning algorithm to predict gt for any given pair of st and at. So this is fine. We have some way of doing machine learning. Now the question is, do we have to wait for all of these rt plus 1, rt plus 2 etc. to be generated before we can get the label, the right label for gt? Because ideally what we want to do is to train the q value to be as close to gt as possible. To do that, we have to first get the correct value of gt, which, unlike in the case of say image recognition etc., you don't just look at the image and know whether it contains a dog or a cat. In this case, to get the right value of gt, you have to wait for all of these rewards to be generated, which is too inefficient. We don't want to do that. So what is the kind of shortcut we can take? We can observe that this expression rt plus gamma rt plus 1 etc. is actually a recursive expression. And how is that? So if we take gamma out, here what remains inside the remaining brackets is rt plus 1 plus gamma times rt plus 2 etc. Okay, so essentially from the next time step onwards, you get the return from that time step onwards, correct? So gt is actually the current time step reward rt plus the discount factor times the return from the next time step onwards. But we already know how to guess what gt plus 1 will be, correct? Because we have an algorithm that gives us for any state and action what the predicted return will be. So if we give it the next state and the next action, we can predict what the next return will be. So on the right hand side, we can use the output of the same algorithm but for a different state and action. And now we can only have to wait one time step to get the label for this uh, network or the machine learning algorithm. So is that clear? So on the left hand side, we'll say the prediction of the algorithm is q of STAT, whereas what we want to try and match or to reduce the error to is the right hand side, which is RT, which we will observe, and then gamma times the q value from the next time step onwards, the output of the same algorithm. And eventually you hope it will learn to a point where these two sides will match exactly. And so you will be predicting the right step reward and the total return from any point onwards. Okay. And this in essence is called a value based reinforcement learning algorithm, where we predict the value of a state action pair and we choose whatever action is giving us the maximum value. And now at this point, we can take the greedy action, right? Because our value already incorporates all of our future rewards. It is exactly the thing we want to maximize. So we can take a greedy call on which action to take. It is whichever action is giving us the highest predicted value, that is the action we will take. So at every time, we will take the maximum value action. So this is all the value based algorithms you get in reinforcement learning. There is a small drawback to this kind of approach, which is that you have to evaluate at all possible actions what the predicted value is. Okay, and this may not be feasible if you have a very large number of actions or if you have a continuous action space. Okay, so in this example we only had three actions, so it's very easy to see that you can evaluate this function st comma x1, st comma x2 and st comma x3. You can do these three evaluations and pick whichever action gives you the highest value. But if you had 1,000 actions or 10,000 actions, this would take a long time to do. And if you had a continuous problem, for example, what angle of the steering wheel should I use in my autonomous vehicle, then you cannot even do this kind of querying. Okay, so you need to have some other kind of approach, and that approach is called a policy based method. So in the policy based method, we won't go too deep into them, but the idea is that you do not give state and action as the input. You give only the state as the input and you get the action as an output. Okay, so instead of having st comma at as the input and the value as the return value, the q value as the return, you give just the state as the input and you get the action as the return value. Okay, and like I said, we won't go too deep into how they are implemented, but it is very similar to the value based method with some mathematical trickery. Okay, let me just take a sip of water and I'll come back. Okay, so since I'm aware that this is an AIML in Python kind of course, I thought it would be interesting to also show you how this uh, all of this framework is implemented in an actual programming language like Python. Okay. And so this is how we will implement the reinforcement learning algorithm and the environment in Python. So essentially, you have two different codes or classes. Okay, you will have an agent class and you will have an environment class. That is easy to see, right? So if you look at this layout and you were asked to make a programming, model of this, you would have a learning agent class and an environment class. So that is exactly what we will do. We also have to define the schema of the entire input and output structure, right? So you have states as the input vector, actions as the outputs, reward is a scalar value which is from the previous time step. You need to track what time step you are currently in, and you have to define some kind of exit condition for this loop, right? You will observe that this is a loop, or the states and actions was a loop. So at some point you have to exit it, and so you have to define what is the terminal state. Either you have achieved a goal or missed it, or you have run out of time to achieve the goal, so there is a timeout. And so what you do is you initially get the current state from the environment. So env is the variable I'm using to denote the environment class. It's an instance of the environment class, and it should have a function called get, which queries the current state of the environment. Okay, so the state will be environment.get. You will then send this state and the current policy, which is whatever the training of q value prediction etc that you have. That model is given as the input as well as the current state, And the agent class, agent is an instance of the agent class, has an act function. Okay, so the act function takes as input the state of the environment and the current policy that you are following, and it will give you the action as the output. Okay, this action will be returned to the environment in the form of a next function, which is going to move the environment forward one time step. So you will see that there is a time step increment here, as well as a reward being evaluated during the forward move, so that your state in the environment will be updated. You will generate a reward, and you will also increment the time step, and all of these things will then get repeated, right? So after this is done, you will go back, and until you have either hit one of the terminal states, so you have hit success or failure, or you have run out of the time steps, you will keep going back to this. You will query the state again, you will take the action again, you will do an increment again. Okay, and then you will go back. So you'll complete this loop until some terminal state hits and you break out of it, and then you will train the machine learning model using the sequence of states and actions that you had and the rewards. Okay, so to train, the agent requires the state sequence that you went through, the actions that you took, the rewards that you got, and the next state that you observed. Okay, so why do you need the next state? It's because of this trick that we had, right? Because we are not going to wait for the whole sequence of rewards to be generated. If we have the current state, the current action, the state reward, and the next state, we are able to generate uh, the loss for the machine learning algorithm. So the policy now is improved by training the agent using the sequence of states and actions that you observed. Right? So you'll see that when you go back and run this algorithm again from the start, this policy will be changed because you have called the train function, you have updated some of the parameters. So this policy will be changed as it observes the sequence of states and actions. And as you play this out for the same state that you observe, you will get a different action because even though the state is same, the policy is different, right? So this is the adaptation that we talked about in the context of machine learning or AI, right? We said that even for the same set of inputs, you can get an improved set of outputs as it learns more and more. So the learns more and more is the policy update, the training call that we have, and this is the way it is collecting the experience on which to train. So clear so far? Okay. Can we do a sound check to make sure I'm still audible?
Yes, sir.
Okay. Excellent. So from this point on, I'm going to go into case studies for the last half an hour or so that we have. Okay, so in case this had become too mathematically heavy, I apologize. But from this point on, it will come back to the real world, and we'll see how this reinforcement learning concept can be used on real world applications. But before we go to real world, just to make it a bit lighter, I want to show you how we can implement reinforcement learning in a very familiar gaming environment of Super Mario. Okay, so what would we do in the case of Super Mario? If we want to train an agent to control what Mario should do, okay, the optimal action that Mario should take, we will observe as state inputs all of the important things on the screen. What are the important things on the screen? It is the position of Mario currently. Okay, where are the possible rewards that Mario can get? What is the location of the enemies so that this is a dangerous position for Mario to be in, as well as what is the time remaining. Okay, the context, time context that you have. So all of this will be given as state input. You will have some kind of neural network learning agent, whatever you want to implement. Let's not go get bogged down with how it will be implemented, but you will get an action as the output, which is what Mario should do next. Should he go move to the right, left, or jump? Okay, so this action will be returned to the environment. So the actual, suppose you say move to the right, so Mario will move to the right, and then you will observe the time steps and the positions, etc. again. And so this will go on in a loop. in order to train or to improve what the outcome is like, you will look at the reward that is generated here, right? Over the course of the episode, you will keep looking at the reward, and that will be given as feedback to the agent to so that it can improve. Okay, so as you play this same state or same stage of Mario again and again, you will get better and better rewards, hopefully, because it will have trained the model. Okay, and there's a quick connection between what optimization problems do and what reinforcement learning does. In essence, reinforcement learning is also solving an optimization problem, but it is spread out over time, over many time steps. And so this is your typical optimization problem, right? You want to maximize the function f, which contains a vector x, okay, by finding the optimal value of the vector x, subject to some equality constraints g of x and some inequality constraints h of x. This is our standard optimization problem. The difference is that in this case, the vector x is composed of all the actions you will take in a sequence. Okay, so it is not a single value. And what reinforcement learning does is populate one element of this vector at a time. In every time step, it will be populating one element so that it can eventually come up with the entire vector, but without using too much computational power. Correct? So the reason optimization algorithms take a lot of time is because you try to compute this entire vector, the optimal value, in one go. So if you run a linear program, the whole answer has to be returned in one go. You don't get partial population of this answer. Whereas reinforcement learning will be doing exactly that. It will do one element at a time. So that's how it is able to generate answers quickly, much faster than traditional optimization algorithms. Right? Now, to make this practical, okay, RL has already got many nice solutions, like I said, in simulation or gaming kind of environments. But to make it practical, the problem is not how to solve a reinforcement learning problem given this formulation. So this is our typical reward plus next time step q value etc. It's not how to solve this, but the problem is how do you even define what is the right state or action that the algorithm is able to take, what reward should get, etc. Okay, so for practical problems, even defining the environment and defining the actual problem itself is a challenge. After that, solving it is what most papers in literature will be doing. Okay, so our focus is usually on how do we formulate this problem when we are given a practical case study and we want to solve it using reinforcement learning. So here's a concrete example of what I'm talking about. Okay, it's a vehicle routing problem, which I'm sure is very familiar to everybody. It's one of the first things we do when we look at optimization. So this is the problem. You have a central depot in the middle here, which contains some vehicles. Okay, each of those vehicles has a maximum range based on the petrol tank that it has, and you have a bunch of customers which have to be served in a given day. Okay, these customers have some amount of time window available, so they will say that you can visit me between 9 a.m. and 12 p.m., for example. So the vehicle has to make sure that it reaches the customer between 9 and 12. Maybe this customer has asked for delivery between 11 and 2, so it can go first here and then here and so on. And there are constraints on how the vehicle moves. So if it's going from this customer to this customer, it requires a certain amount of fuel and it takes a certain amount of time and so on. Okay, so the goal of the algorithm is to minimize the distance traveled by all the vehicles put together to serve these customers within their timing windows. This is a very kind of well known problem. But if you think about just formulating it, so if I was, TCS and I was solving this for a customer, if the customer gave me this problem in mathematical form, I would be very happy and I would be able to solve it. Our issue is that the customer can only explain the problem in words, and we have to make the mathematical formulation for it, and then it becomes non-trivial, because it's not always the case that this vehicle, you just exactly want to minimize the distance traveled. Sometimes the customer will say, oh, we do want to minimize the distance traveled by the vehicles, but we also want to improve the service perception by customers. Okay, so if you can serve the customer within 90 minutes, that's also good, but at the same time I want to minimize the distance traveled by the vehicles also. So now we get into qualitative discussions of what a good solution looks like. Okay, so even for something as simple as this, making the mathematical structure, what is the objective function, what are the exact constraints, and writing them down mathematically is the challenge. After this, we can solve it either with traditional optimization or reinforcement learning, as the requirement may be. Okay, so I just wanted to use this example to show you what the difference between a practical solution and more academic kind of solution would be. So this, in essence, summarizes the issues we have that we are especially trying to address in practical RL. Okay, the first is, how do we even make a copy of the environment, right? So in the case of Super Mario, which was the example we looked at, it's very easy because the environment is given and there are specific rules as to what can and cannot happen in that environment. Okay, so while Mario is running, he cannot get a phone call from Luigi, asking him to come back with vegetables, or something odd like that. But these kind of things happen all the time in real life problems, right? So in this example, I've shown one of the case studies that we have solved, which is port planning. Okay, where the goal is, yeah, is there a question? Okay. So the goal is that if you get an empty ship that comes into the port, what is the minimum amount of time you can load the ship in so that it leaves as fast as possible? Okay, and to get the minimum amount of time, you have to define the sequence of containers that goes on the ship, and these containers have to be conveniently located. Right, so a container on the top of a pile is good because the crane can directly move it to the ship. The container on the bottom would be bad because the crane would first have to move all the containers on top to the side, then pick up the container and put it on the ship. So it takes much longer. Okay, so the complexity now is that this ship is not alone in the port. There is going to be a number of ships being loaded by a number of different cranes. And so you might say that I have identified the next 500 containers that I want to load on the ship, but it might turn out that by the time you load the first 5 or 10 containers, some 20 or 30 of your other containers have gone away. They have been picked up by other cranes and put on other ships. So now you have to quickly recompute and adjust to this, right? So many odd and strange things can happen in real life problems, and so even coming up with a good simulation to train the algorithm on becomes difficult. So that's our first challenge. The second challenge is that the dimension of our problems can be huge. Okay, so in the case of chess, you might think of chess as a complex problem, but you have to understand that this is a fixed 8 cross 8 board with a fixed type number of pieces which have well defined behavior, right? So the knight can always go two and a half places, the rook can always go only side by side or top to bottom, etc., right? So the number of things that can happen is limited, and so your dimension size is limited. Whereas if you look at this problem, which is railway scheduling, then the number of trains on your railway line can change every day. The number of tracks can change, and there can be a huge number of trains and tracks. Right. So just in India, you have about 12,000 trains on a regular day, and to schedule all of them, it's a very large dimensional optimization problem. So handling this large dimension space is also something that becomes tricky. The third is computational effort, which I mentioned that towards the start of this talk also, that we want to use a reasonable amount of compute to solve these problems. Okay, so to give you the contrast, there is a very famous bot from OpenAI, which is a company that Elon Musk owns. Okay, this bot has learned to play against a team of humans in a strategic game. Okay, so this is called Defense of the Ancients. The game is called, and it contains 5 or 6 different characters that you can control and all sorts of strategies that you can take to win the war. Okay, but the difference is that the company was able to train on 60,000 CPU cores, okay, and using 256 GPU chips. Okay, so essentially they were playing about 300 years worth of games in a single day. Okay, and they were able to do this for I think 2 or 2.5 months before they were ready to play against a human being. So you can understand that as human beings, we are using far less experience than this to be able to play at an expert level, whereas the computer is essentially wasting a lot of the information it is generating and using only a small fraction of it to learn, and that is why it needs so much computational resources. So one of the very key things that we are trying to do in my team is to see how efficient we can make this training so that you use as much of it as possible, and so you have to use that much less training to learn good policies in the first place. Okay, and the fourth challenge that I'm looking at is very unique to practical problems, which is that your policies or the actions that you take have to be very transparent to scrutiny. Okay, they have to be acceptable to the users, and essentially you have to be able to explain why certain actions were taken given the states that were observed. If you don't do this, nobody will use your system even though it is completely optimal. Okay, you might be doing twice as good as any other system that has been used before, but if the actions cannot be queried or explained, then nobody will want to use it. Okay, and this is very unique to practical problems because in in context like gameplay, you actually do not want your action to be scrutinized. You want to do surprising things, whereas in real life you do not want any bad surprises. You want to be very predictable and regular so that people trust your system. Okay, so in this example, it's for inventory management. We have been able to show what the requested inventory replenishment will be for a given combination of inventory level and forecast demand. Okay, and we are able to show that okay, if this is the inventory and this is the forecast, then this much inventory will be requested and so on. So we can actually show the user that there is a nice smooth gradation between what happens in the observation side and what action is taken, so that the person feels comfortable taking whatever recommendation the system is giving. Okay, so the last few slides will be based completely around case studies that we have worked on. These will be more and more real life case studies. So first is more topical, which is how do we optimize lockdowns with more quantitative justification than is given currently. Okay, so today, unfortunately, we are heading into another wave of COVID-19. But this work we started in the first wave itself, and at that time, all over India, there were a lot of lockdowns being declared without much of a, discussion about what exactly the effect of these lockdowns was going to be. Okay, it wasn't particularly wrong at that time because somebody had to take a decision and do it. But what our thinking was that if we can actually predict the quantitative effect of these lockdowns in terms of balancing health impact and economic impact, and if we can train a reinforcement learning agent to decide whether a given district should be locked down for the next week or not, then people might be able to trust the decisions a little bit more than what we did last year. Okay, and so this was a model that we developed. So on the environment side, we had a simple population based network flow model where the amount of connectivity between any two districts in India was approximated by the product of the two populations and the square root of the distance between them. Okay, so the bigger the cities and the closer they are, the more strongly connected they are. At the same time, we also had a disease progression model. So as you go from susceptible to exposed, to infected and asymptomatic, or infected and symptomatic, and so on. And so with these two models in place, we said, okay, in simulation, if we can detect the number of infections in a given district, okay, and these are only the observed ones, the ones that become symptomatic and actually take COVID test, and we know what is the network connectivity between pairs of districts and how strictly the lockdown is going to be enforced and so on, can we define and train a reinforcement learning agent that decides whether to keep an individual district open or closed for the next week? Okay, and we were able to show, using the real world data that we were getting and the predictions of the model that we had. So in this case, the real world data is red and black, the predictions are in blue, and what we are predicting is the number of active cases over time. Okay, so we were able to show that, first of all, given the policy that was implemented, our model is able to fairly well match the real world data. So we have some kind of validation of the model output. And then if we can train this reinforcement learning agent to improve the lockdown decisions based on the number of symptomatic people in the whole population, the number of symptomatic people in the district, and so on. We had, I think, 7 or 8 different parameters we were looking at. Then can we actually show that we could have improved the outcomes based not just on the health impact but also on the economic impact? Okay, and obviously, I mean, this was an approximate and kind of proof of concept case study, but we were hoping that eventually in the future, if this kind of thing happens again, then we will have something in place that is more justifiable than just doing this based on gut feel. Okay, so we have also done a reinforcement learning based controller for Konkan Railway, which, since you are also joining from Karnataka, you will be very familiar with. So it goes all the way from very close to Bombay, all the way down south, nearly into Kerala. And the idea is that initially, when the Konkan Railway was developed, it was a single line track, and it was expected to carry about 50 trains per day. But today it is carrying over 90 trains a day. So obviously there are a lot of delays on the system every day, pretty much every day. And the complexity comes when every time you have a delay, it is a slightly different place and a different train that gets delayed. So you cannot have fixed rules for how to recover from these delays. So that's one problem. The other problem is that because this is a single line, up and down, you have to share the tracks. A delay to one train leads very quickly to delays to other trains, which are called secondary delays. So our goal was to define a reinforcement learning agent which could minimize the spread of these secondary delays by bringing trains back to the timetable as quickly as possible. And the way we did this was, first of all, by not looking at the entire length of track all the way from Maharashtra to Kerala. We said, let's look at a local horizon, a few tracks in front, a few stations in front of a given train, and a few stations behind the given train, and decide based on what those track occupancies look like and whether the trains are coming towards you or going away from you. Based on these observations, can we decide whether the current train should move out of the station or it should wait in the station? Okay, and this will be done for every train that is running on the railway line, one at a time. And using this kind of simplified approach, we were able to show that there is a potential for around 20% reduction in delays overall, especially the secondary delays, if we do this more quantitatively than what is currently done. So currently you have human controllers which are looking at separate pieces of track, and the issue with that is that you don't know, as one controller, what is happening in your neighboring region. Okay, so you might take a certain set of decisions that reduce the delay in your section of track, but when you hand over to the next section, that person is disadvantaged. Okay, and so these delays kind of go back and forth. Whereas with this kind of reinforcement learning algorithm, you should be able to optimize the whole railway line together, and so you will get much better outcomes overall. Okay, we have also used this reinforcement learning approach to pack bins more efficiently. Okay, so the context here is that if we look at a postal company or a courier kind of company, then you get a lot of parcels to this. Each parcel is of different size and shape. And what the company does is pack all of these parcels that are going from one city to another, say from Mumbai to Chennai. They will pack all of them in larger bins, and those bins will be transported to Chennai, where they will be unpacked again, and then they will go to their individual addresses, delivery locations, right? So this is typically done by humans right now. So you get these parcels on conveyor belts. They are packed by humans into bins, and then they are sent on. And the humans can have very different performance based on how well they are trained. Okay, so you get in real world data that we have seen humans do as little as 50% volume utilization of the bin. So only about half the bin is packed properly, all the way up to nearly 90% volume utilization. Okay, so there is a very large amount of variance in human performance from person to person, and most companies want to reduce that. Okay, so one of our customers came to us and said, it's okay even if you don't hit human expert level performance, 90% kind of utilization. If even if you can consistently do 80% and eliminate the kind of humans we have which do only 50%, then we'll be very happy. And so the first step for that is that you get robots to do the packing itself. Okay, but this robot needs to be told where each parcel should go. Right, the robot is just capable of picking up a parcel and putting it wherever you ask it to, but where should you ask it to put the parcel? So this problem we solved using reinforcement learning. We were able to figure out, looking at the incoming parcel dimension and the current state of the bin, where the existing parcels are, etc. We were able to figure out how to pack it as smoothly as possible so that the volume utilization is maximized, and we were able to get about 82% volume utilization on average. So this was a pretty good outcome. If we return to the vehicle routing problem, again, our current performance is that if we look at certain benchmark problems where the optimal solutions are known, then our algorithm is about 15% worse off, but it is taking less than 1,000th of the computation time, okay, to come up with the kind of solutions that are 15% below optimal. So, from a practical perspective, this is a fairly applicable system. So, we don't have to wait 2 hours to reach a solution. We can start, moving those vehicles within a few seconds. So, that is the kind of outcome we are interested in. And then the last couple of examples I have are from the retail industry, the supply chain industry. Okay, the first of these is what we call accelerated fulfillment of e-commerce orders. So, e-commerce are the online orders that you place on Amazon, Flipkart, etc. And if you go to, say, Amazon.com and you're trying to book a certain item for next day delivery, typically you will have a deadline that shows up, right? So, book in the next 3.5 hours to get next day delivery. And the way this 3.5 hours is calculated is as follows. So there is a certain number of processes that have to happen on whatever item you're buying before it can be delivered to you. Okay, so typically it has to be located in the warehouse where it is sitting, and it has to be brought to the packing station in the warehouse. If you are looking at a very large company like Amazon, this warehouse can be as large as a very big stadium. So it can take up to 2 hours for this parcel just to be found in the warehouse and put on a conveyor belt and brought to the packing station. After which it is packed and put on a truck in, say, maybe half an hour, and then the truck travels to your doorstep in another 3 hours. Okay, so this 2 hours plus half hour plus 3 hours gives you a 5.5 hour time required to put it on your doorstep. and so accordingly you get the deadline that shows up on your website. So what we said was, if we want to reduce this time required, the fulfillment time required, without actually touching any of the individual processes, okay, we don't want to reduce the 2 hours, half hour, 3 hours, but we want to reduce this total to 3.5 hours. So how do we do that? We said, let us predict what people will be buying on the next day. Okay, and those predicted items we will optimize to say, okay, these are the items I want to pick early on, okay, on the previous day itself, and start moving them to the packing station. So even before you have purchased, say, a given t-shirt, your t-shirt has been picked up in the warehouse and it is already moving to the packing station. And so what happens is, when you actually place the order, you just put a label on that t-shirt and you instantly put it on the truck and send it to your home. So that way it comes to your doorstep in 3.5 hours without changing any of the processes. Okay, so now you'll be a bit skeptical and say, how do you know that I'll be buying this t-shirt? Okay, and the answer is that I don't know that you specifically will be buying this t-shirt, but I do know that somebody will be buying a given type of t-shirt. Okay, so to give you an example, if there is an India World Cup match coming up, a large number of people are going to buy India uniforms, right? So I may not know whether you or your neighbor or his neighbor is going to buy an India uniform, but I do know that in your apartment complex, probably two or three India uniforms are going to be bought. So I can start sending that item towards your apartment complex even before a person actually pays for the item. So that is essentially what we are doing. Okay, so this we have done for a UK based retailer already, and reportedly they are pretty happy with the outcomes. And finally, before we stop, I want to leave you with the thought that AIML systems do not have to operate alone. Okay, it's not like you have an environment and you have an AIML or reinforcement learning algorithm working on the environment. You can actually have a number of AIML agents working together. Okay, so in this case, what we are looking at is a retailer with a very large supply chain. Okay, so the retailer buys items from farms or from factories, puts them in a very large regional warehouse. Then there are items that get shipped to local warehouses, which are in your individual city. From the local warehouses, they come to individual stores or they are delivered directly to your doorstep. Okay, so solving the entire movement of items through the supply chain, there could be more than 1 lakh different types of items. Okay, solving the movement of all of these through the entire supply chain is impossible, at least with current resources. So what we have done is, we have converted each store, each local warehouse, each regional warehouse into its own reinforcement learning agent. So from the perspective of the regional warehouse, everything except for itself is part of the environment. Okay, so the local warehouse is part of the environment, the store is part of the environment from the perspective of the regional warehouse. Similarly, for the local warehouse, all of the stores and the regional warehouse is part of the environment, whereas it itself is learning. So what happens is, all of these individual reinforcement learning agents learn to optimize their own rewards, but at the same time, with the way we have designed the problem, they also learn to cooperate with all the other agents in the system. So the stores, the local warehouses, the regional warehouses essentially coordinate to move the items through the supply chain in a much more cost efficient way. Okay, and so this is called a multi agent reinforcement learning formulation. Again, the concept itself is not new, but the application to a practical problem is the novelty part of it. And this is also part of a TCS product called Optimera and has already been put into practice in one retailer in the Netherlands. So it's something we are very proud of. Okay, so this is my final slide. So to summarize what we have been looking at, we said reinforcement learning is one of the three types of machine learning, but it is focused specifically on taking optimal actions, not just predicting something or analyzing data. And we said that from a practical perspective, solving the reinforcement learning problem is not really as hard as actually formulating the reinforcement learning problem. So deciding what the states, the actions, rewards, etc. should be for a given problem. And the way we do this is by consulting domain experts throughout the entire project. Okay, and so that they are there in the design phase, they are there in the execution phase as well. uh, we build these environments from scratch so that they capture all the relevant detail but do not capture everything that could be captured, because then it would become too complex to train. And we have to make whatever states and actions that we have, states as inputs and actions as outputs, we have to make them understandable to humans so that there is a certain amount of trust that the humans have on what we are doing. And we also sometimes have to optimize, or rather tune what we decide is the reward for the system or the objective value. It is not always clear cut, so sometimes we have to go back to the humans and say this is what we see and so on. So yeah, with those kind of thoughts, I leave you and we can have maybe a few minutes of discussion. I think we have 5 minutes left. Am I
Like,
still audible? Yeah.
yeah, yes, yes, sir. Yeah, like I just put, like anybody can unmute themselves and they can ask queries. So
Yes,
from
please.
my end, there is a small query. Like we have seen a pretty good number of solutions by TCS, and they are like doing a magic in specifically the supply chain management. So
Mhm.
I've just a small question, like what specific tools do you use for solving this?
So there are two answers to this. Okay, so on the research side, we tend to use basic Python language and the libraries on top, TensorFlow, PyTorch, and so on. Okay, because it gives us the most flexibility to actually know, answer some research type of questions. But to do deployments, there are already tools in the market which can do training of reinforcement learning agents very quickly. So Bonsai is a solution from Microsoft which does this. So you build your simulator and you connect it to their platform, and it can train the RL agent on its own. At least that is what they claim. We have not really gone deep into whether the claim is correct or not, but so you can do deployment very quickly, and you can do, if you want to answer some research type of questions, you can do it in basic Python also.
Hello.
Yes, I can hear you.
Yeah, yeah. Sir, there's another small query that we have. Like, it may not be with the transportation. So we have one problem. Like normally, VTU is connected to 200 colleges, and there are around 20 different set of branches who take exams. So, and the exam schedule normally happens over a period of 2 months. Can we use some kind of reinforcement learning and plan in a very optimized way
Yes.
so that the
So
time? Yeah, yes, sir.
yes. So what I would say is that you can use reinforcement learning for sure, but if you have the time available to solve the problem using normal optimization methods, they will give you better solutions. Okay, so the place where we use reinforcement learning typically is when you don't have time to wait for an optimal solution. So you need a relatively good solution, but very quickly. So that is when we tend to use reinforcement learning. If you have
Thank,
a
yes.
couple of months left, right? So, and you can say maybe start 1 week in advance and do the scheduling, then you can probably solve it using a traditional optimization method, which will give you a better solution.
Right, sir. Right, sir. Thank you, sir. Thank you, sir. I
Sure.
just put the mic. Anybody from the participant, if they have their questions or queries, they can ask by unmuting themselves, or they can put it in a chat box, or else they can forward to our email ID, which is with them. and the same queries will be forwarded to Harshad sir. Thank you, Harshad sir. Thank you.
Thank you. Thanks for the invitation. Bye.
So, thank you, Harshad sir. It was a wonderful session. Yeah, am I audible, sir?
Yes, yes, I can hear
Yeah,
you.
yeah. So, thank you very much, sir. It was a wonderful session, what we had, because all the sessions, whatever we had it, so they were mainly been talking about the basics, about what is the machine learning, how the uh, learning happens and all. Whereas today you're taken up to the new level, sir. It was very good because all that industry perspective it was been added in the today's session, like how the industry works and where exactly we apply that reinforcement learning. Because supervised, unsupervised, all that learnings, we know it where we apply and when we know the output. But whereas this reinforcement of which when we want that optimal solutions and with all your real-time examples, what you work with the TCS, so that is exceptional, sir. Because most of the time, these industry people they won't share such information with the people outside. Whereas today you have taken that task and you have shared all the real-time examples of what the TCS takes up in case of this machine learning, like the logistic, the retail industry. So what will be the future? How exactly it will be? So it was a wonderful and a memorable session for all of us, sir. So we
Thank
thank
you.
from the college, that is Gndecb Engineering College, be the Computer Science and Engineering Department. And we hope that we will have a long-term association with you so that in turn, not only the faculty members, but our also students should also get benefited of it. And definitely, if you permit us, we will contact you and we can have some sessions for the student also, sir.
Sure, sure. Certainly.
Yes. Okay, sir.
All right.
So
Thank
thank you,
you.
sir. Thank you for joining the session, accepting our invitation, and taking your time from your busy schedule to engage the session in this 1 week AICT IST refresher induction program, which was on machine learning with the Python. Thank
Thank
you,
you.
sir. Thank you, sir.
Thanks.
Thank you, sir. Thanks, sir. Yes.
Next session ಯಾವಾಗ next session 11:30 Hello. 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 Very good morning to all of you who have joined for this session. Um, I'm Professor Rashekar Gaiton on behalf of the Department of Computer Science of Gndecb Engineering College and on behalf of all the participants who are participating in this 1 week session. I'm extremely delighted and it's my privilege to welcome Dr. Jyothi Prakash Singh as a resource person for this today's session for 1 day refresher course on machine learning using Python. Sir, we are extremely happy by your presence and you are delivering um, a topic convolution neural networks. Convolution neural networks in this session, sir. So, I would like to introduce Jyothi Prakash Singh to all my participants. Jyothi Prakash Singh is an assistant professor and head of the Department of Computer Science and Engineering in National Institute of Technology, Patna, India. Sir has completed his PhD from University of Calcutta. He has co-authored 7 textbooks and 1 edited book with reputed publishers such as McGraw-Hill, Elsevier, and Springer. Sir has published more than 35 international journals in publications in leading publishers and more than 50 international conferences proceedings. Sir was involved as an investigator in the Mitsui-sponsored project to develop algorithms for spam calls or fake calls in telephonic conversation. His research interest to focus on social media mining, deep learning, information security, and speech processing. Sir is also a senior member of IEEE and ACM. And sir is a life member of Computer Society of India and IST and Institution of Engineers. Sir is an associate editor of International Journal of Electronic Government Research and guest editor in Multimedia Tools and Applications by Springers and Complex and Intelligent Systems Springers. Because Sir's outstanding contribution, Sir was been awarded S4DS Data Scientist Academia Award by Society for Data Science in 2020. So this is a small briefly introduce about Jyothi Prakash Singh. Now I request Jyothi Prakash Singh, sir, to take over the session. Over to you, sir.
So thank you, sir. Thank you for the nice introduction and good morning to all the participants, the organizer, and it's really a good theme to have. So I have chosen a topic, convolution network. Now, I hope I am audible.
Yes, sir, you're audible, sir.
Thank you for confirming. So convolution neural network, this is now a buzzword. Everyone knows about convolution neural network and they are using also in their different applications. So I will give you a very basic idea about convolution neural network, then switch on to how this CNN also can be used in case of say the speech or text normally, how we can use it in text applications, although these are normally very good for the image applications. And then I will also demonstrate you some experimental details how we can really with the text, how we can implement a convolution neural network. So let us move on to the topic. What is convolution? So basically convolution is a mathematical operation and 2 functions, say f and g. It expresses in terms of the electronics, it expresses how the shape of one is modified by the other. And exactly if you look at the term, the convolution, it refers to both the results of a result function and the process of computing it. Both are called as convolution. Normally in case of images, this convolution is used to extract features because this workshop is on basically machine learning. So you know in case of a machine learning, a good amount of effort should be given to the feature engineering. So how we can extract features. And that's where this convolution neural network plays a very important role. We can extract a lot of features, good features, which we human being cannot, probably sometimes cannot extract. Those features also can be extracted from images. So I will just give a brief idea exactly how convolution helps us to extract those features. Like if, say normally before these convolutions were widely used, or deep learning, introduction of deep learning, with images, people used to find out. If you look at any image, say, let me just show you an image here first. Say if we have an image like this, then what are the things or what are the features we can extract from the images? So probably if you do just image processing tools, then you can find out how many horizontal lines are there, how many vertical lines are there, how many curves are there, and later on we can think of, okay, if those curves are say joined each other with each other, then we can get some sort of shapes. So how many such shapes are there? So traditionally, people used to find out they had a fixed operator, like Sobel operator, Previtt operators, and so on. So we use using those operators, people used to find out different edges. So probably there is one operator, and say we have been given an image. Then once I apply one operator, which will find out or which will give us all the vertical edges, and then that can be listed as a feature. Then we can apply another operator or another, say, window or function kernel, and we can get all the horizontal edges. Similarly, edges slanted at say 45 degree, so slanted at 60 degree, and similarly for all possible cases we can find out. Now these things, in fact, can be very beautifully and very elegantly done using a convolution neural network. Let's see how it goes on. I hope all of the participants, those who are attending, they know about convolution, but still we can just refresh it and then I will move on to the other topic. So given this image, so this image is a 6x6 image, and say this is basically called as a window or say kernel or sometimes filter. So say we have a filter which is 1 1 1 0 0 0 1 1 1 in this direction, or if you read it horizontally, then 1 0 1 1 0, sorry, this should be -1. Just there is a mistake in this slide. So this will be, this is -1. So 1 0 -1 1 0 -1 1 0 -1. If we put this image, so convolution is basically putting this filter onto the matrix, onto this image matrix, and then element wise multiplication is done. So this 1 will be multiplied by this 3, this 0 is multiplied by this 0, this -1 is multiplied by 1, and similarly the next element and so on. So and then they are added up. So we take a sum of all those. So basically this is 3 into 1 plus 0 into 0 plus -1 into -1, sorry, 1 into -1 and so on. If we sum all of them, we get -5. Then we shift this. Is this? Is okay. So next we shift once. So next is we have shifted, but this shifting not necessarily has to be 1. It can be of any size. So any shift. So next we shifted it, and then we can again similar process we can follow. So now this time it will be 0 into 1 plus 1 into 0 plus 2 into -1 and so on. So we'll get -4. Next, and similarly if we keep on shifting, so once the complete row is complete, the horizontally it is completed, then we move shift in the vertical direction 1, and we continue this one. So if we continue, we will get something like this. So this was the image. And this is another, in fact, you can say this is one sort of feature or intermediate image, which will capture all the vertical edges. So basically, if we see this image and this image, then we can see that in this image, the resulting image, the vertical edges have been highlighted. Similarly, so you can see here, it's a very beautifully crafted example where we can see the vertical image. So if we have, now here you can easily find out that there is a vertical. So there is something higher, say basically brighter, and this side we have a darker area. So if we multiply with this one, we will get something like this. So this was the original image. This is our filter. So it's 1, then 0, bit gray, and then -1, so it's more darker. So the image which we will get is something like this. So now you can find, you can easily see that this vertical edge is highlighted. So this vertical edge is highlighted. Similarly, if you change it, this is vertical. If you do it in this way, 1, 1, 1, 0, 0, 0, -1, -1, -1, what you will find out is you will highlight the horizontal edge. So this is vertical, and if we so that was the original image, and if this is the image 1, 1, 0, 1, 1, 0, 1, 1, 0, then 0, 0, 0, and this side this. So here we have both edges, vertical as well as horizontal edges. So if we apply horizontal edges first, we will get something like this. Then you can apply the vertical edges and you can get this. So this is the example which I have already shown. So by repeatedly using this sort of operators, we can find out the vertical and horizontal edges. Then exactly how this convolution is helping us. Now you think that instead of, so if you think of now that I have to find out all possible edges in an image, then first I have to manually see the image, and then I have to find out the operator which can really find out the edges for me. So if we are trying to find out vertical, we have something like this. Horizontal, we have seen 1, 1, 0, 0, 0, 0. Sorry, 1, 1, 1, 0, 0, 0, -1, -1, -1. If we want to find out some, say, I mean to say, the angles are different angles. So if I put something like this, say 1, 1, 1, and then 0, 0, 0, and say -1, -1, and then -1. If we put like this, then we can say that we will find all the edges which are like this. If we reverse it, if we make it say this way, if we make it this way, 1, 1, 1, and then -1, -1, then we can find out edges like this, and so on. So in convolution neural network, exactly what we are doing. So we view all these values. So these values -1, 1, 0. So this value, let us view these values as something to learn. Or in fact, we say that, okay, I have now these values 1, 1, 1, -1, -1, -1. These were experimentally evaluated. So people have done the experiment and then they found that this value will find out the horizontal vertical edges. This will find out slanted edges. Now, instead of experimentally finding out this, let us make them as our learning parameters. So say if we consider that all these weights, so W1 to W9 are the weights, then these weights can be tuned to find different types of edges. And that's what will be our features basically. So these weights, now we are going to learn these weights. So instead of writing 1, 1, 1 or -1, -1, -1, and sometimes it can be 2, 2 also. If you want to highlight it more, you can make it 2, 2, 2, 0, 0, 0, 2, -2, -2, -2. This will highlight it more a bit further. So what will be this value? What should be the better value which will find out or which will give me the best features, all possible edges? So we make it basically a learning rate, learning parameter. Now remember, one such filter can find out one sort of edges only. One filter will never be sufficient to find out all possible edges. So with one filter, we can find out, say, the horizontal edge, With another filter, we can find out the vertical edge. So we have to apply these filters in a sequence, or basically in a huge numbers. So we have to apply these filters, say 100, 200, 300 filters. So if we apply 300 filters, probably those 300 filters will find out 300 different types of edges. If we have 50 different filters, they can be tuned to find out 50 different types of edges. Okay, so that's the idea. Then this was where we told that, okay, if you just see what we did, if we have a 6x6 image and if we have a filter of size 3x3, then you can easily see that the image size is reduced. So if we have 6x3 and filter is 3x3, the resulting image is 4x4 only. If somehow if we want to make the size, or if we want to keep the size of the image intact, then it's obvious that we have to use padding. So how many padding we should use? So normally in case of padding, if you want to find out how many padding, that means we have to add some number of rows and columns, so that after convolution the result is same as the number as the size of the original image. So you can find out the number of paddings, number of rows in fact, which is filter size minus 1 by 2. So now if you see that if we have an image of size 6x6, if we add basically if we have a 3x3 kernel filter, then we have to use 3 minus 1 by 2, that means 1. So if we add one size of padding on all sides, we'll again get a 6x6 image as a result. That's the. So now without padding, if we do convolution, we call it as valid convolution. Why I'm talking about this? Because these things are given as a parameter when you write a program. So even if you are calling a keras function or all the functions, you can pass these things as an argument. So if you are thinking of, let my size of the image be decreasing, then you can use the convolution, or the convolution which you are using is valid, and this is by default. So if you do not supply anything, it's by default a valid convolution. Other one is same. So other parameter you can pass is same. So if you want that the output size should be same as my input image was, so then you can supply same. And if you are supplying same, then automatically these functions, the API, whatever you are using, they pad the image with that numbers, and then so that the result of the output image size is same as the input size. Then we have a concept of strided convolution. So sometimes we want to, okay, let this image is very big and let it be decreased, or there are some areas which we do not want in specific applications. Then we can have strides. So stride is basically like in first image application or first convolution application, I told that the first place where the convolution will be taking place is this one. And then the next one was this from here. But if we say that my stride is 2, then we can shift to 2 places. We can supply this, or we can say the stride to be 3, 4, 5, anything. So if you supply the stride, then obviously your image size will be decreasing more, because you see that if we stride is 2, then this is the first convolution, this is second convolution, and this is third convolution. So 6x6 image will be now reduced to 3x3 image only. So it's similarly in the vertical direction also. This is how it will go. So if we, in a summary, if we find out exactly what happens if we supply all the stride and padding, then if we have an n cross n image, and if we have a s cross s, f cross f filter, and stride size is s, and if say we denote padding to be p, then we can find out the resulting image to be n plus 2p minus f by s plus 1. So this will be the resulting image. We can find out the p also. with by the formula we have discussed already. So this will be the resulting image. Okay, so this is very basic idea of convolution. Now, so with convolution we talked about, okay, with convolution we can get different types of edges, but not all this. Some of those edges might be basically representing a fraction of the edges which is already covered by some other area or some other nearest pixel, because we know that in a pixel several pixels basically make up a visible area. So when we do this, it might happen that we have now got some features which are very close to each other, and then we want, okay, let me find out the prominent area so that later on we can, the size can be reduced and we can work better. So we do an operation called as max pooling. So there is not necessary that this should be max pooling. Also you can have a mean pooling, you can have average pooling. So there are pooling. So in general the operation is pooling. So pool, that means we are extracting something. So again we define a filter size. So say in case we have a filter of size 2 cross 2 as shown here, and if we say that we have a max pooling, now in this filter there is nothing. So in max pooling we are not learning anything. So if you think of the takeaway so far, then in convolution, when we are performing convolution, we are learning the parameters. So all those weights are specified there, and those weights will be learned. So those weight value will be updated. Whereas in case of pooling, there are no weights applied, so there is no learning as such. So while we will see the summary, we will see that in pooling layer, there is no trainable weight. We are not training anything. We are just pooling, extracting the values. So if we say that we have a filter of size 2 cross 2, a kernel of size 2 cross 2, so you can say that this is 1 2 cross 2 area, and we will take the biggest value. If it is max pooling, we will take the biggest value. So we'll write 9 here. In second, we have 2 1 1 1. So 2 is the largest value. So we'll take 2. Similarly, 6 from this, 3 from this. So now this feature vector can be reduced to this. We can think of mean pooling also. So in that mean pooling, it would have been 1 1 1 1. So all will have been ones. Some people have even tried with the average pooling, where they can take average of this. I think I have an example of that average. So in average pooling, we can have 12, 13, 15, 15 by 4. So something, say 4 point something or 3.75, something like this. Then here we have 5 by 4. So 1 point something. Here we have, and similarly we can go on. So we can find out the average. No, so some people can say, so no, I will not take just one prominent value, but I will take the average of all the neighboring pixels. So you can go with average pooling also. But max pooling is by default, and this is the pooling type which is used by most of the researchers. But that obviously doesn't stop you to experiment in your case. So if you are trying to write your own experiment or experimenting in some scenario, you can try with the other pooling options also. So as I told at the start itself, that one say that in that case, say one pooling, and pooling, say it was just one plane, basically one say matrix or something, a single dimensional, say two-dimensional matrix, just two-dimensional array or matrix. So but normally when we talk about images, we have multiple, say we have 3 channels in an image. So red, green, blue. So how the filters will be designed? So filters will be designed. The third dimension will always be the last dimension of the filters. So filters, so here you can experiment. So like here we can say, if I say, so here we can use 6 by 6 by 3. Since we have 3 channels, this filter will be, this side will be 3. But there is no bounding on this one. I can even define a filter of size, say 5 cross, say 5 cross 5. But the last dimension will be 3 only. Last dimension cannot be 5. And then this convolution occurs like this value will be convolved with this one. This will be convolved with this, this will be convolved with this, then this area will be convolved with this. This area will be convolved with this. And similarly, this area will be convolved with this. This area will be convolved with this, and so on. So the convolution will be volume wise. So volume wise, all the values will be multiplied. So this value will be multiplied by this value. The this green value will be multiplied by this green value. This blue value will be multiplied by this blue value, and then they will be added, and finally we'll get. So now you can see that the dimension is reduced by a huge amount. So we had an image of size 6 cross 6 cross 3, and if we apply a filter of size 3 cross 3 cross 3, then finally what we will get will be an image of size 4 cross 4 only. So many values will be now condensed into one. So this whole channel, this vertical dimension, this dimension will be merged into one value. So this is, in fact, this value is the operation of merging operation of all these 27 values here in this case, 9 plus 9 plus 9. Right. So this is how this convolution does. But you might have seen in your experiment that once you convolve it, you also get something which is a multidimensional. How we achieve that? So as I told at the start itself, that one sort of convolution filter will only filter or will only give you, say, one sort of edges or one sort of feature. But you want to extract different types of feature, all possible features. So for that, you need to require you need to convolve so many values. So if you write a program, whenever you write a program, you might have seen that you supply a filter of size, it's a number of filters. So they ask for number of filters like 64, 128, 100, 200, 500, any number you can supply. That means this operation will be done so many times. So like here I have shown two different types of or two different filters. So this first filter will have certain weights. So 27 weights are here, 27 more weights are here, and so on. So all these are trainable parameters. So when we convolve, when we do the convolution, actually these are the weights which are being trained. Now how they are being trained, I will be coming to that. So these weights will be trained. And similarly, if you supply, say, if you say that, okay, I will be using 128 convolutions, such convolutions, then 128 such filters will be there. And everyone will have 27 values. So the total number of trainable parameter in that layer will be 128 into 3 into 3 into 3. That means 128 into 27. And after operation, each 128 will give you something like this. So say 4 cross 4, 4 cross 4. And now if you put all of them together, one after another, you will have a resulting image of size 4 cross 4 cross 128. So again, it will be a volume like this. Okay. So putting everything together, what we can say that we have an image and then we apply a convolution. And then as I have told in the previous slide that we apply some number of convolutions. So all those number of convolutions will give me some image like this. Then again, we apply some number of convolutions. And then after that, we flatten. We normally have a flatten calling of flatten function. So what flatten does is it converts all the possible matrix into a single dimensional array. So whatever values we have, it puts one after another. So it makes a single dimensional array. And after that single dimensional array, we have a simple neural network. So a dense neural network. And finally, we have the output. How really it works? So given a training set, so we give certain images and then we give some labels with that. So say if we are just trying to classify whether it is a cat image or not. So we have two class classification, say cat versus dogs. So we have say 1,000 images. So consider a scenario. So we have say 1,000 cat versus dog images, and this number of classes is 2 only. So at this first layer, if you supply and say each image is of size say 128 cross 128. 128 cross 128. So at the first layer, really this image will be, since this is color image, this size will be 128 cross 128 cross 3. And then you apply some number of convolutions. So say I have applied say 100 number of convolutions. Then this resulting image will be basically 126 cross 126 cross 100. I hope I am clear. We had original image of size, this cat image is of size 128, 128 and 3, this because this is color. And I have applied 100 convolutions. And each convolution is of size 3 cross 3 cross 3 because this is last one is 3. So that will be. So if we apply a kernel or a filter of size 3 cross 3 cross 3, the resulting image which is coming here will be of size 126 cross 126 cross 100 because I have applied 100 such filters. As we discussed in the just last previous slide, that we apply one by one filters and all those pages are put together. So that will give us the third dimension. Right. Then sometimes we do pooling. So if I say that I will pool it by a 2 cross 2 such area or pooling filter, pooling kernel. So if we apply a pooling of size 2 cross 2, then this will be nearly halved. So this will be in fact halved. So this will give me 53 cross 53 cross 100. Okay, so while we are doing pooling, in fact, we are not taking volume wise. We are taking only through in each layer. So if we apply a pooling of size 2 cross 2, then the result will be 53 cross 53 cross 100 only. Third dimension will not be disturbed. And so on, it will come and finally it will basically it will be flattened and finally we will get some result here. Say this is an image of cat and my output was that this is a dog. Right? Because the weights were not initialized properly, so it's an initial weight, random weight. So this is obviously not the trained one. And initially when we supplied a cat image, the result was a dog. So the model told that this is dog image. So obviously there is an error. Now how to minimize this? So what we do, we create a loss function here. So we calculate a loss function. A loss, like any simple neural network. So we calculate a loss, and this loss is basically, since this is a two-class classification, we can easily compute a binary cross entropy loss. So once we have a loss function, then following the back propagation technique, so those losses will be transferred back, or based on those losses, the weights of these layers will be first trained. So based on those weights, those losses, those loss value, the weights will be updated here. Then subsequently the weights at this layer will be updated. Then subsequently the weights at all the convolutions. So all the W values which we were talking about, that filters. So all the weights of all those filters will be updated at every layer. And all those weights now will change slightly. Then we'll supply another image. So this time again, say we supplied a cat image and again it told dog, because that cat image will be slightly different. And again it told dog. So again the same thing will be repeated and so on. So this basically keeps on being repeated, and we know ultimately the weights will shift, and then that will basically align with the features of the cat and along with the features of the dog. So that's how basically in a convolution neural network the whole training is going on. So this is I have already told that cost function, and obviously we'll use a gradient descent to optimize parameters to reduce J. That's the target in any machine learning algorithm, in any neural network technique. That the philosophy is same. The only thing why we use a convolution neural network instead of a simple dense neural network is, if you analyze, in fact, I will write the program, I will give you the program and I will show you with the program that the most of the weights, so in a normal neural network, you will get weights in the range of say 10 lakhs, 12 lakhs, 15 lakhs weights to be tuned. And you will see that if you keep this, if you see these weights will be higher, because here we have connections from each node to each other node. So that's really a very big ask. That ask of that number of parameters is quite high. Whereas in case of convolution, if you think of, because these weights are shared, so in case of convolution, the number of weights is relatively lesser. That's one of the major motivation behind using convolution instead of a simple dense neural network. These are some of the popular convolution neural networks. Okay, so popular convolution neural networks are like LXNet, everyone knows. So in case of LXNet, just we can see here. So this image is of size, normally the input image which is to be given into the LXNet is 227 cross 227 cross 3 because color. We apply say convolutions of filter size 11 cross 11 with a stride of 4. Since we apply convolutions, we apply basically the filters of size 11 cross 11 and we make a stride of 4 after every convolution, the resulting image is 55 cross 55 and we have applied, so they have applied 96 such filters. So that's why the resulting image as the resulting feature, whatever you say, will be 55 cross 55 cross 96. And then they do a max pooling of size 3 again with a kernel value of 3 cross 3 and a stride value of 2. So that will reduce this image to 27 cross 27. But as I have told that the max pooling doesn't disturb the third dimension. So third dimension remains 96. Then they move on and then next convolution they do is 5 cross 5 but this same. So 5 cross 5 same means they have used padding there and after padding they did the convolution, so the first dimensions will remain same. So 27 cross 27 because this is the same convolution. But the last one will be disturbed because it will be basically 5 cross 96. So 5 cross 96. So all those 96 dimensions, third dimension will be reduced to one layer. And total number of convolution filters which will be used here is 256. So the number of parameters, if you estimate, so just if I give you an estimate. So here the number of parameters, trainable parameters will be how much? It will be 11 cross 11 cross, since this dimension was 3, so 3 will be there. 3 cross, and how many filters were used? So there were total 96 such filters. So 96. Excuse me. So these many parameters or weights will be there in this layer. Then at this layer, if you find out the weight or the number of say parameters which will be used is 5 cross 5 cross, it will be 96 cross 256. I hope I'm clear exactly why these values are coming in this way. 5 cross 5 because the filter size is, but the third dimension will be 96 because there will be total 96 third direction and resulting is 256. That means 256 such filters were used. So if you just count, and this is some of the layers only. So there are many layers in LXNet, and if similarly if you count, you will have a number of. So again max pooling, and then again same convolution and so on, and they continue. So this way they are finally in the final layer, last layer, we have 9216 number of outputs. So this is the input and this is output, and in between we have this. So ultimately the loss will be computed here. And these laws, based on these laws, the weights of this layer, then this layer, then this layer, then this layer, and layer, and so on, it will continue to be updated. So this is one part of images. Next, as I promised you, that I will also talk about the text portion, exactly how the convolutions are used with the text. So before going further, let me just give you a very basic idea of the text processing, exactly how things occur in text. So I will just move on to slightly the practical demonstration, and then I will come back to this theory again and that convolution also. So if you see what I have, the demonstration, what I have put here is, we have a file called as SMS spam. This file is available online for free. So we have some messages here, and these are either ham message or spam message. So we have some messages here, you can see here. So these are the messages, this one, and sorry, this one, and these are the labels with that. So I write, I think these are very common things to write this file, SMS spam collection. This is the name of that file. And as you can see in this file, there is nothing. So no label is there in this file. So no heading was there. And these are separated by tag. That's what I'm writing here. So import pandas as PD and then read pandas.read CSV. Separator is /t, and since there is no label given with the data set, I am giving my own label. So I am giving the names equals to label and messages. And then I will run this, sorry. And this is what you will get. So you have now the message, which I have just shown you on that prompt. So you have the label here and you have the messages here. And then I can separate them out. So I want to now make two arrays. One is with the label and the other one is with the message. So message is kept in a variable called as text, and the label is kept in a variable called as class label. So if we separate them out, now done, and then you can separately check them. So class label, you can check ham spam, and if you want to just check that really the messages are coming into text, you can type and you can see that these are the messages coming into that. And then what we are doing is we are categorizing, we are just converting these messages, these labels, because so far with that convolution neural network, or in fact any neural network, you can know, that these values will be ultimately converted, has to be converted to 0 and 1s. So this is what we are doing here. We are taking that this is the class list, ham and spam, and I'm converting them into some sort of categorical values. So categorical values means there are two classes, so ham and spam. So we have two values, so one is ham and the other one is spam. So if a message, like the first message was, I think ham, so we can put ham, we can represent that as like this. So if a message is spam, we'll make it as like this. And this is basically the categorical representation of the labels. So that's what we are doing, and you can find out the results here. So the final label is something like this. 1010 means this is ham. 01 means it is spam. 10. So against ham it is either 1 or, so whatever is the value, it will be 1 against that value. So that's the simple idea. So after this, it's taking a lot of time. I do not know why. Okay. So I hope really okay, so it has been done. So this is the label now. And then if you see those messages here, we had a lot of other text like star and so many other texts will be there. So we are pre-processing them. So what we are doing is we are pre-processing and we are removing all the special characters like explanation, quotation, hash symbol, ampersand, this. So all these things, they are kept into filters. So everything will be removed. We are making everything to be lower, and we are splitting anything where there is a space, and taking them, storing them as a token. So that's what it will do. And then you can see here that the vocabulary size is 910. That means this message, what we saw here, in this message, there are 910 unique words which have occurred. Okay, so if you go through this whole one, you will get there are 9010 unique words. So normally to represent a word, what normally is being done is every unique word is kept in an array, and you can see in this next value index. This is what you can get here. So like every word has a position. So it's an array, and you can consider it to be an array. So the first word at the first position is containing the word I. The second position is containing the word to. The third position is containing the word you. Fourth position, word A is there. Fifth position the. Sixth position you. Seventh position and. Eighth position in, and so on. So every word has now got a position. Every word. So all 10,000, 9,010 words, basically, you will have those things. It's all are not shown here, but you can check. You can store them in a file, and then you can check that all words have got a position in an array. Excuse me.
ಜಯವರ್ಗೆ ಇಲ್ಲ ಅಂತ ಹೇಳಾರೆವಾ ಎಲ್ಲರೇ ಕುಂತಿ ಏನಾರ ಮಾಡ್ತಲ್ ಮಮ್ಮಿ ನೀ ಸೀದಾ ಉಗುರು ಒಕ್ಕಟ ಆಮೇಲೆ
Okay, so
sorry sir, I muted it. Yeah. You can continue, sir, please.
So that's how we can now represent each word. So I hope I'm clear exactly what I'm trying to say. The words, every word will be, so we will create an array of the whole unique words, and every word will have a position in that word. And if you want to represent now the first sentence, say the first sentence is in X, yes, X takes the sequences, text to sequences. Then in X, if you want to represent the first sentence, so X0, you will have something like this. That means the word which is occurring at 49th location, it was go, and then 471. So all those words are occurring into that sentence. So you need now think that in that first sentence, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So only 22 words are occurring, but this will be represented by an array of size 910. So now you have an array of size 910, and every sentence you think of, every sentence will have some 10, 20, at most 30 number of different words, 30 to 40. So this will be a very really sparse array, basically sparse representation. I hope I'm clear exactly what I'm trying to say. It will be a very sparse, because your every sentence is now going to be represented by a vector of size 9010, and in those 9010, some of the entry will be 1, the words which are occurring in that sentence, and other entries will be 0, and that the number of zeros will be too high. So like you can see here, so X0 is in terms of that matrix, and text 0 is the real word. So you can see that 49, what I was trying to say, 49 is go. Now you can see the first word was go, and the 471 until. So you can see, you can find out here 471. 471 until. So now you can find out a correspondence between this word, this representation. This is giving you position. So basically internally what it will be represented, or what you can think of is, okay, there we have a matrix, we have a vector of all unique words. So starting from 1 to 9010, and then these entries are made 1, rest entries are 0. So all these entries will be made 1, all other entries will be 0. And that's a huge wastage of the whole thing. So if you want to see the whole matrix or the whole representation of the whole word, then this is how we can represent it. Okay. So only these are 0, rest will be 0. But the problem with this is, even with this the real problem with this representation is, first of all, all these are a lot of entries are 0. So this will be a real sparse matrix, the whole text representation. And the second word is, there is no reference. So there is no similarity. Like if I say hotel and motel, both are representing more or less similar concept, but they will have different location. You can now estimate, although that example is not here, but you can think of that motel will have a different location and hotel will have a different location. And there is no way we can find out, or we can relate them together, that okay, these two are representing similar concept. To find out that sort of idea, people have come up with called as embedding vectors. So all this representation, so what we have representing it in terms of say some numbers, so zeros and ones, what we can do, we can convert them to some number of, say, regular zeros and ones by something called as embedding. So there are so many embedding technique. Just obviously this class is not about embedding. So what I'm just trying to show you exactly after embedding, because those examples will also come into that text said the textual part, the presentation what I have. So what embedding does is, it converts that 9010 values or representation to some compact form. And this compactness is done in such a way that if two words are close to each other, they occur with each other, then they will have a similar value. Okay, so that is called as embedding. So embedding is shown here. Here we have already created, by default, creating an embedding. You can see here we have an embedding layer, and then we have converted a vocabulary size +1. Why this 1 is added is because we have not seen all unique word of the world. So in 9010, we have all the words which have occurred into that message, plus 1 position we keep for all unknown words. So if it comes across a word which it has not seen, that those words will be considered as to be unknown words, and for that we are keeping a place. So vocabulary size +1. And we are converting now the whole 9011 to a dimension of 100. So we are representing that 9011 values to a dimension of 100 using that embedding vector length. How embedding is being done is basically something called as with friends relationship. So like the people you are close with, if I have to find out, say, how someone is, then probably their close friends will give us an indication that okay, his close friends are of this nature. So probably outline, or you can say some of the natures you can find out about that person, any person. So same idea works in the case of words also. So if a word has occurred with these sort of words regularly, or in a similar context, then this word also has a similar meaning. That's the basic philosophy of embedding. So after embedding, if we say see the results, which is not shown here, unfortunately. So then this value will be 100 dimension values, and this will be a continuous value, which I will again now move on to the presentation and I will show you. So this is how it will represent. For example, I have taken only 4 dimensions value. So now you can consider that all those 9011 values is now mapped to some 4-dimensional values, which is the embedding values. So in that 4-dimensional values, now this ease can be represented by some values like this, playing by some values like this, well against Sri Lanka today. So we have now a sentence which can be represented by this sort of matrix. So India is playing well against Sri Lanka today. This can be represented by a matrix like this. I hope I could have given a very basic idea and established the fact that how exactly we are representing these things. And then in a convolution, what we do, what the similar with the similar nature of convolution, what we have did in case of the images, we can also think of the convolution in case of the text. But there is a difference, and there is a big difference between in a convolution for convolution in text and the convolution in images. What is the difference? In case of images, we told that the third image is basically a 2 by 2 convolution. So a convolution of 2 by 2, that means we have a row and column. But in text, we only go with rows. So we do not have a notion of column. In fact, the column is similar to the third dimension in case of images. So whatever number of columns we have, the second dimension of the kernel or the filter will be always equal to that. So if I say that, okay, I have a filter of size in this example, the example what I have taken, if I say that I will take a filter of size 2, then this is virtually filter of size 2 cross 4. Why 4? Because this 4 corresponds to this value. Okay. And 2 is basically the number of rows. So if I say that, okay, we will use a filter of size 2, then first time we will convolve these two values. Then if we make a stride of 1, then the next, these two values will be convolved. And the next two values and so on, it will continue. In this example, I have taken a convolution of size 3. So the real convolution will be of size 3 cross 4. You can see here. So this is my filter. And in this filter, if we take this value, random value I have taken, these weights, these are the weights which will be learned. This we have already discussed in the previous context. So these are the weights which will be learned. So if we keep this sort of weights and if we convolve, so first of all, this will be convolved with this, and we will get something like this. Here we will see that when we are convolving, we can write it as India is playing. So these three values are convolved together and give certain values. Then next will be is playing well. So is playing well. Then well against Sri Lanka. So sorry, playing well against. So playing well against well against Sri Lanka and against Sri Lanka today. And now you see that all these four dimensions has merged into one. Then what we can do, we can take another filter of size say 3 and again repeat. So with different weights. So again you repeat that same process. You will have one more columns here. And repeat that same process. You will have more and more columns. That's one way. Then that's the way. So normally if we apply 4 kernels, again this will become, so 4 filters, we will have 3 more columns here. This is called as gram. So in text, people talk about n gram, 1 gram, 2 gram, 3 gram, and so on. So normally when we say that this is 3, filter is size 3, so this is basically a 3 gram structure. That means 3 words are taken together. If you apply a filter of size 1, that is 1 gram. If you apply a filter of size 2, that is 2 gram. If you apply a filter of size 3, that is 3 gram. If you apply a filter of size 4, that's 4 gram. Normally, in case of text, people normally go with not more than 5, because not more than 5 words occurring together make any bigger sense. They are very infrequent, in fact. So 1 gram, 2 gram, 3 grams are very common. So because some names also are, mostly 2 gram is very popular. But again, when we experiment with all different possibilities, all different grams, all different combinations to get some meaningful ideas. So that's how we normal, in case of normal convolutions, if you go in text, you will see that this dimension is normally 100. As I told that the pre-trained embedding which is available on the net, like globe embedding. So one popular embedding technique is called as globe, GLOBE. OVE, and this is presented, this was done by Google. Then we have fast text. So fast text. This is another embedding which is done by say Facebook. And then there are several other embedding techniques. These two are very common. In Globe we have English, and the dimension, if you see there, they are available in the dimension of 50, 100, 200, and 300. In fast text also we have similar, more or less similar dimensions. So these are available as a pre-trained, but any day you can train your own, as I have told, as I have shown in my example. So you can see here we have tried another convolution, something like this, and then 3 convolution, 3 filters I have applied, and 3 results I have shown. That I have already explained that if we apply 3 different filters, we will have 3 different columns like this, and continue. Okay, then we can do a pooling. So again, we can go with max pooling or mean pooling or average pooling, as you like, and say, if we say that the whole pooling, if I go a pooling of the max pooling with this whole structure, then you can find out column wise, this is 0.3, this is 1.6, and this is 1.4. So we can find out this sort of pooling, or we can take smaller snapshots and we can do pooling on that, and then we can repeat the convolution. So this is an example of average pooling. We take average of everything and then divide it by the number of rows we have. This is a convolution with a stride of 2. So first of all, so here you can see, so it's 5 and then India is, so 5 India is, and then since it is a stride of 2, then next we will come here. So is playing well, and then again we will come here, directly, Sri Lanka today, and then 5. So Sri Lanka today and 5. So with a stride of 2, what we have already seen in case of images, we can go with a similar structure or similar thing in the text also. Then convolution with text, local max pooling, and stride of 2. So first of all, we have this text, and then we applied the convolutions. So 3 convolutions we applied, and then if we say that, okay, I will go with the max, first there was with stride, and then now I want to go with the local max pooling. That means I will pool between these two layers. So these two rows I will pull, then these 2 rows, then these 2 rows, and then these 2 rows. So with those poolings, this is what we will get. And now this can be taken as a feature, and then again next layer of convolution can be done in a similar way. So this is one architecture we presented while we were doing, this was an architecture by Kim, which very similar architecture we also used, and since this was very well shown here. So we have the sentence here, then we apply different number of filters, we get different maps, then pooling, and then concatenate again, and then we can do our sort of prediction. Experimentally, in fact, we implemented this sort of network for helpfulness score prediction on a consumer reviews. Like all of you, we have seen in Amazon or Flipkart, we have reviews, and those reviews has helpfulness score. And only the higher helpfulness scores are normally shown at the top if you are thinking of, or if you are finding out, going for a review of a product, to read the review of a product. Then these are, in fact, already I have explained how exactly we are reading all these values. This is encoding, that example also I gave you. This is a pre-trained embedding example. So in the last example, or in the live example, what I demonstrated was the embedding was created by our own technique. So it was a embedding which we were creating. And in this case, you can see that this is a pre-trained globe model we are taking. So this is downloaded from the Google. I think the site is not remembering to, I'm not able to recall that. But you can find out, search this, and this will be available. So there is a text file. We open this text file, and then we find out for every value now there is already a defined entry. So we load that and we create an embedding matrix. So in our example, the work which we have done, they had around these many words, and so we loaded everything. So this is, and then we created this embedding vectors. And then now let's move on to the example again. So this already I have run, and now I will explain exactly what is happening here. So given text, as I told that we will convert the embedding, and you can now check. That's what I was talking about my whole talk duration. This will have better visibility now. So in case of embedding, we have 9 lakhs 1,000 parameters. And then the program, if you see that we are creating a model of type sequential, then we add the embedding layer, and then we add a convolution 1D. So normally it's a 1D convolution in text. If we have images, then these convolutions are normally a 2D convolutions. Okay. And then we talked about the number of filters, how many filters we will use, the kernel size, how many kernels, what will be the size of the kernel, and then activation, although I did not talk about the activation at that particular time, but since it is a neural network and every time the input it passes through, there will be a activation. So in case of any neural network, that's the basic architecture we know. So we have, so this is our neuron, if this is our neuron, then we know that there will be a summation value, and then there will be an activation function here. So in case of convolution neural network, mostly the activation which we keep is ReLU, but not necessarily. In fact, there are several versions of ReLU also. A ReLU is an activation function which most of you might be knowing. Still, I'm just giving a very brief discussion. So ReLU looks like this. So it's a linear function. Whatever comes, it will be just passed through. So say why we take linear, why we do not take sigmoid or tan H? Because with ReLU, you can see that you will always find out gradients. Whereas sigmoid, etc., you will get, so like if it is a sigmoid, something like this, then in sigmoid, if the output is somewhere here or here, you will not get any gradient value. And if the gradient value becomes 0, then your weight updation will be very low. And since in convolution we have so many layers, we have a huge number of layers, normally 5, 10, 15, 20. So going so back, and if this value, this gradient becomes 0 or very small, then multiplying all those values will give you 0, and ultimately there won't be any weight change. So normally we prefer ReLU. Then we do a max pooling of size 5, that means it is 5 cross 5, and then we flatten it, and then we add 256 dense layers. So in convolution, now you check the total number of parameters is 38,528. How it is coming? Because our input was of dimension 100 cross 32, I think. So the input, which is output shape, is 30 into 128. So we have 30 into 128 into total number of inputs where, how many inputs were there? Sorry, 100 to 30. And plus all those weights. So this is the number of parameters. Then max pooling, we do not have any parameter. Then flatten, we do not have any parameter. Then in dense 2, we have so many parameters. So you check, that's what I was telling. That in dense 2, we have the maximum number of parameters. Compared to convolution, you can check that in dense, the number of parameters are too much. Then the next dense layer, so we again reduce it. And finally, we use a binary cross entropy because we have two classes only. Optimizer, we can use any optimizer, but here we have used Adam. And the accuracy was only checked to see how good or bad it is performing. So once we have this model, so this is how we define a model. And then after that, we can fit that model. So fitting is basically training. So on any machine learning models, I think you might have been for last 2-3 days. This is the 4th day. In fact, the course is going on, and in every Python course, you have been told about this fit function. So in any machine learning algorithm, basically you have 3 things to do. First thing, you have to call the instance of this model. So we have created an instance of the model, which is in this line here. So we have created the instance. If it is a pure machine learning algorithm like Bayesian network or say SVM or decision tree, you can just call those functions. And then you call a fit function. So fit function will basically do all this sort of training or fitting or finding out the optimal parameters. And then you do a prediction. So next you call model.predict. So calling the model, fit, model.fit, and model.predict. These are the 3 things which are in Python. If you are going with Python and you are developing a machine learning algorithm, these are the 3 key lines. Rest other lines are basically the pre-processing and how you see the results. That's all. These are the 3 lines which are really doing that machine learning part. You can say the heart of that whole problem. And before that, there are some code. After that, there are some code. Before codes are used to basically find out or pre-process your input. After code, the code after this predict is used to just check the prediction or find out the score. So if we say like here, if we run this, and then you can check the results. So this is the prediction results you are getting. Obviously, since the results was the level was categorical, so it will be 0, 1, 1, 0, something like this. So you can see here that is 9 point something, it is 2 point something, and then we call a argmax function, and with that argmax, this is argmax. So with argmax, we convert this value into this one. So 1, 0, 1, 0, 1, 0, 0, 1, and so on. And then you can call, or you can use a classification report and print the precision recall F1 score and so on. So this is what the precision recall F1 score. In fact, you can find out the confusion matrix accuracy already. I think we had calculated here also. Validation accuracy was 0.98. Here also you can check, and that's how basically you can go ahead with any text. Images I have not shown here deliberately because I know images codes are very readily available, and almost all those who are working with images, they can easily do it. So this is how we can summarize the model. So this line print.model summary will give you the summary of the model. So my request will be to all of you, those who are especially early age researchers, those who are just starting their research, are thinking of doing something, whether they have written some program or they are yet to start or they have just started. Whenever you are developing a model, you just check this one. Okay, how many parameters you have, and then there are 2 things you can check: the total number of parameters, trainable parameters, and there are certain non-trainable parameters. Now the question is why these parameters are non-trainable and why these are trainable. So in fact, these are non-trainable parameters because if you remember, so the code I told that we are using this pre-trained word vectors from Globe. So there is no need to train this embedding. So although there is an embedding layer, you can see here there is an embedding layer. Even in this one also, you can see that there is an embedding layer we have called, but those parameters are not trained. So in that embedding layer, the weights are already fixed. They won't be changing. So whatever weights is already fixed, that weights are coming through that Globe model. We have fixed it. Similarly, if you are using transfer learning, so in case of transfer learning, if you have a network, you are calling, you are creating that whole model as well as the whole weights. But obviously, according to your own case, you have to change. You have to train some of those parameters or some of. Okay, so there is a question: what is transfer learning? So far, if you think of, so if you think into this, let me just give you this example. Let me just give, because this is a very popular one, and people use it for a lot of examples, a lot of cases: AlexNet, GoogleNet, VJG16, and all those. So one thing is that given this model, you can recreate this model in your lab. So you can create a network of this many convolution, max pooling and everything, and you can train it with the inputs what you have. But remember it, the number of parameters which is going to be in this case will be too high. So, and why to reinvest or say reinvent something which is already there. So there is a concept of transfer learning. So in case of transfer, what we say, exactly this model is available and known to everyone. So anyway, we can create the model. The problem is, the real difficulty is the weight, because that's where you invest your time, that's where you invest your money and your resources. So since the weights, in this case, the people have also made available the weights. So you can download this model as well as you can download the weights which are for this model. So at every layer, all those W values, their weights are available. So you can download it from the net. And once you download it, this whole network, the whole weight, the trained model is available to you. So you have a trained person, trained model available to you. But as you can see that this model is trained for classification of 1,000 different objects. But you might have an example or scenario where you want to just say classify disease into two classes. So whether the disease is there or disease is not there, like in COVID. So there is a COVID or non-COVID with chest X-ray image. Say for example, I'm just taking. So this thousand output is of no use to you. Then what you can do, you can again create one more layer here and classify it into two classes. So as soon as you create one more layer, so that layer has to be trained first. And then, as I told, that CNN is mostly a feature extractor. So those features, so at first layer, if you see that first layer, you will have some sort of say edges. Second layers, those edges will form a curve and some sort of say circular structure. Third layer, you will have the curves organized better. So if you take an analogy of human face, you will have say circular face here, you will have eyes here, lips here, and so on. So initial layers are very coarse feature and last layers are very fine features. So if you think of using this network for medical cases, so initial cases or initial things will be more or less similar, but last things has to be tuned for you. So there is a there is a technique called as transfer. Say in transfer learning, we can fix some of these parameters or some of these layers to be non-trainable, and we can make some of them to be trainable. So if you say that okay, these three, 1, 2, 3, 4, these I will train. So you can make them trainable, and you can, with your own example, these weights will be trained. Rest will be untrained. So there won't be any weight change in those cases. So I hope the transfer learning, someone was asking for transfer learning, is clear. I was able to answer your query. Yes, it is. It means using that pre-trained model. It means using pre-trained model and change few parameters to suit our application. That's right. Absolutely right. Okay. So with that, I think we have almost at the end of the session also. It's around 12:50. So I think we were here. So this is what we have already told, that model.fit, and then we can find out the history, we can plot this mean squared error and so on, as I told, best accuracy. And this also you can plot, in fact, model or summary you can do, you can in fact plot the whole model. And in this network, in this image, these features are available in Python, Keras. So input, output, everything you can get. So that will better make you understand, and even in paper you can write it. So with that, I would like to acknowledge this. Most of the slides are taken or adapted from Professor Andrew Ng's course, and some of the slides were also taken or inspired by the Christopher Manning courses on natural language processing. With that, I would like to thank really for your kind attention and involvement. So I would like to see or say get your questions. suggestions, feedback, whatever you say.
Thank you, Jyothi Prakash Singh. It was a very like a good presentation, excellent presentation. And sir, from my end, I have got a small question. Like
Sure.
in one place, like where you have not applied log-seq function, but applied a ReLU function. But normally, when we work with a neural network specifically, we ask like you have a good range and ask to go for a log-seq function.
Okay. In this convolution, text convolution you are talking about? See, as I told, no.
Yes, sir. With reference to text convolution, you have
It's not
applied a ReLU
text
function. So,
yes, please repeat your question.
so let us assume like I am not applying that, and if I am still applying, let us say the log function, then only I may get a good range even for that.
Okay, so I think all of you might have heard of, say, what is called as say, vanishing gradients and vanishing, VANISHIG, vanishing gradient. You know about this problem, vanishing gradient? Exactly what happens in any neural network. Say if we have a neural network like this, any neural network you think of, convolutions are not exceptions. Any neural network, you have these weights, you have connections like this. You give your input at this layer and you get your output at this layer. So that's the convention. In neural network, CNN also we have the same thing. So if we give a X, we give a, we get all these X's are given and finally we get Y hat. And then we compare this Y hat with the real Y what we have. So a loss function is computed with this. So what Y hat we have got and what Y I should have achieved. Now, based on that, that loss now has to be minimized. And those, so in any neural network as a whole, why this loss has occurred? This loss has occurred because of the weights which are there. So all these weights which are there at different connecting points, they have created this loss. So all these weights are responsible for creating this loss, are yielding this loss. So if we want to reduce this loss, these weights has to be minimized. And normally the weight minimization is done through an algorithm which is very popular called as backpropagation. Backpropagation, okay. So in backpropagation, this loss is first fed to this. And we take, so this, we take a gradient of this loss. So we take a delta of this loss gradient, and then based on that delta, negative of that delta gives us the direction where we should go. And this delta multiplied by the current input gives us the weight. So weight nu, so we write normally weight nu is weight old weight minus eta or learning parameter, what we called as, then delta, and then the x1. So this is what we normally do. Now next time, so this weight will change. The weight which is here will change. Now next time we'll move in that direction, and then we'll want to change these weights, the weights at this layer. Then this delta will again be multiplied by another delta. And so on, it will keep on multiplying by different delta, because now what is the gradient of this? That has to be multiplied by the whole value. What is the gradient of this? And that's where this problem occurs, vanishing gradient. Now you think of if this delta becomes very small. So if my initial delta is say 0.2, then the next layer delta becomes 0.003. 0.03. Next layer the delta becomes even smaller, so 0.00005. and so on. So and now you can see that they are being multiplied. So if you keep on multiplying smaller numbers, ultimately this will tend to be 0. So what happens now with this figure, you can think of here you will have a change in the weight. Probably here also you will have some change in the weight. But as you move beyond this point, say, these weights will not change because this value, because all these are multiplying factor and this becomes nearly equal to 0. So as they become 0, your old new will be W new will be W old. That means there won't be any weight change. So virtually in a network of say length or say depth 10, might be you are only able to change the weights of 3-4 layers, last 3-4 layers. The earlier layers are not changing their weights. So virtually those are wasted. Am I clear? So that's the problem called as vanishing gradient. And why vanishing gradient occur? Because this delta value. And now if you take, let me clean this one. If you take a ReLU function, so a ReLU function looks like this. It's a linear function. So if you calculate gradient, because sorry, this should be straight line. I'm sorry, due to stroke it changed. So since it is a straight line, you will have gradient calculatable at or a good gradient at every point. Whereas sigmoid or tan H or all those sort of functions, they look something like this. So if the error value is coming here or here, that means if you are either at the two, the classification is very good, more or less so. So the error, this gradient value will be very low. Almost you will have 0 gradient or very small value, say like 0.00006. So you have a gradient like here, something like this. Even at this point, your gradient will be very good into this area. Other than that, the gradient will be very small. That's the value, that's the reason that in most cases we have a smaller gradients and which gives us a problem of vanishing gradient. Or so that's why people normally use ReLU function with CNN or with dense networks. So if you have many layers, it is better to use ReLU. In last layers, you can use softmax or say logistic or whatever you say, sigmoid. But if you have quite a depth, then ReLU is a better option. That's the reason.
Thank you, sir. Thank you, sir. You reviewed the complete backpropagation algorithm in one this example. So, thank you, sir. I got my answer for this question. I expect participants, if you have any queries, you can unmute yourself and ask sir the question. It was a very informative, very excellent session, and we are grateful to sir for giving his time and joining us for delivering the session. From behalf of the management, staff, and the committee members who are organizing this specific induction refresher program, I'm very thankful to Jyothi Prakash Singh. Sir has given a very wonderful session which gives more insight into like where our research direction can go in. And also, sir, the examples that you have taken were excellent, and I think we will definitely use the knowledge which is shared by you, sir. Again, because we have got 1 minute to go, if somebody has any question, we can take it, or we have to.
Sir.
We will be. Yeah.
Sir.
Yeah.
Okay. This, sir, I have only one question regarding the transfer learning. Because I use that transfer learning for my own project actually. In the one question is, in the last layer we are applying the softmax and this AlexNet and GoogleNet, RaceNet, all these transfer learning models are used for the 1,000 categories of image classification, right? So if I use this transfer learning model to detect whether there is a COVID or non-COVID, then in the last softmax, instead of passing the value as 1,000, is it okay to pass the value 2 because we want COVID or non-COVID? Is it right, sir?
That's what I told that there is a structure, like there is something which is already built and we are transferring it or we are taking it pre-trained.
Yes.
So what we can do, if you have a bigger tap, basically, this is a tap, and if you have a small place where you want to, a small bottle to be filled up, you have to create your own path from that bigger tap to your bottle. No.
Yes.
You have to create one more layer, basically. In a single sentence, if I say you create one more layer, so you add one layer into that network, where you say that there is one more dense layer which is of size 2, and then that 2 will be your answer.
Okay. Thank you, sir.
I hope
yes, it's clear, sir. Yes, sir.
Okay. Thank you so much.
Any other questions from the participants? If there are no questions, I take this opportunity to from heartily thank Dr. Jyothi Prakash Singh. You have highly enlightened us with your examples, which basically starting from the simple convolution, taking an example of a Sobel kernel and diagonal and vertical kernel, and taking it to the level where words were convolved. It was a very informative presentation, sir. We look forward for your similar cooperation in your future endeavors. If there are any queries from the participant side, they can be mailed back to the organizer's mail ID. We will forward it to JP Singh, sir. Sir would be very happy to share his knowledge by answering such queries. Well, again,
Sure.
Thank you, sir. Thank you, sir.
Thank you so much for organizing this, inviting me, and this nice audience. Questions, because this question, in fact, which enlightens the speaker. He exactly
Yes.
it's very difficult to speak to a computer or to a screen. It's really very difficult. But I'm glad that there was some questions and people were really interested in that. So thank you so much. And I have already shared my email ID, and I will share the presentation to the organizers. They can say distribute it to all the participants. So thank you.
Thank you, sir.
Stay safe. I'm leaving. Okay.
Okay, sir. Okay, sir. Thank you.
Thank you, sir.
We thank all the participants. We thank all the participants for actively participating in this session. Our next session will be at 2 p.m., which will be handled by Abdul Rahim, and we will be continuing with using Google Colab. Sir has shared any examples? Sir has not yet shared any examples. As we mentioned yesterday, we are contacting him. If the examples are shared, they will be mailed to your respective mail IDs. Thank you again for joining this session, right? And we will join back at 2 p.m. Thank you. We are now pausing this recording and also the session.